haven't done a stream in a while. I've been working on a couple things behind the scenes. I think the last time I did a stream, I was working on Implish, which is, or I guess I was working on my parser combinators. So all of that, both of those things are meant to, Implish is a programming language and the parser combinators are parsers for parsing languages. All of that is meant to run on a virtual machine called B4. So I'm building a course that is all about programming and teaching programming from the ground up, starting with a virtual machine. And there are many different versions of that virtual machine that I've implemented in different programming languages. So I can actually bring up the page if you want to follow along. It's on GitHub at github.com /B4. That is the name of the system, and I have implementations in J, Free Pascal, Lil, JavaScript, and Godot. And this is the Lil version. Lil is a very high-level programming language. It is the scripting language of Decker. Decker is a HyperCard clone here. What you're looking at here is Decker. It's really good for prototyping things. It gives you like a presentation tool and a programming language all in once. These are all little pieces of the system that I've been working on, and it's also really nice that you can actually just take this and upload it somewhere. So if you go to tangentcode.com, there's actually a sneak preview of this thing up here. So if you go bigger, you can see it. Maybe zoom in, and you can actually play along with a lot of what's here. This is not exactly. I don't keep this up to date. This is not the final version of this. This is pre-release here, but it is up there on the web, and you can get it from GitHub as well. But the nice thing about Decker is that you can run standalone on your computer, or you can just save it as an HTML file, and it includes all the source code for the JavaScript version of Decker, and you can just get all the stuff you want, even the show toolbars. You get all this stuff. You select here, you say style. That's always what I do when I set up. Now you can zoom in and play along with this thing. I don't even think I have the version that has the arrow keys for navigation. That's not. Eventually this will be up there and on a good place. Anyway, I'm rambling. So my intent is, I guess I should elaborate on this. My intent is to make a course for programming, and it's going to be a bunch of these videos, actually scripted videos, not me rambling like this and just making up as I go, but actually, have a script and plan it out and make it really nice and edited. And so that's what the goal is. And then for each one of those, there'll be like a corresponding deck you can use to play with it yourself, or some kind of online presence, online kind of thing you can do. You may have seen my other videos where I'm working on a testing environment that's intended to be the eventual thing where you'll be running code in the cloud and whatnot. But I figured I'd start with just the story I wanted to tell, which is let's have this virtual machine, let's build some stuff on top of it. And the first thing I want to build on it is a basic input-output system. In my mind, BIOS means a lot of things for different people, depending on what system you're on. But in the DOS days, BIOS was a bunch of assembly routines that would run on your Intel machine, and they would allow you to do things like put a character on the screen. I don't know if that's not exactly the same thing, because this is a different kind of idea. But basically, in fact, there's even a file in here called about. Maybe I'll run through that real quick. So about BIOS, basically, you have this machine here, and it's intended to be something that runs atop another computer programming language. We talk about portability being, the word portability tends to mean it runs on Linux, it runs on Unix, it runs on, runs on Windows, runs on a Mac, right? That's portability. It used to be portability would be it runs on this kind of machine, this kind of machine. Now all the processors have the same, compiler infrastructure. So if you can run on one of them, you can run on the other. But what happens if you want to write code that runs on top of the language you've written on the stack, right? So you've got your technology stack, and then say you've got an application like Blender, you've got an application like Firefox, you've got an application like OBS that I'm using to stream here, and you want to script it. Well, each one of them has its own little stack, and they're all little towers. They're silos, right? You can't connect them. So my thought, one of my motivations for this is to make a virtual machine that runs atop all these different systems, and so it can run on top of Decker, and it can also run in your browser, and it can run. There's a native version of it that is written in Pascal, like I said, and that runs like in the, in the currently runs in a terminal, right? So the Linux environment, like a traditional terminal kind of thing. Although I also have, a graphical version for that. Anyway, so the idea is that it's not necessarily a computer, and so the BIOS is not necessarily going to have a screen, right? Like it could be something you're using to script a game. It could be something that you could be using to control an application that you've built. For example, I want to add a scripting language to something I've built in Rust, right? So I have this thing called Bex, and I want a scripting language for Bex, and it has one, but it's really tiny and clunky, and right, I'd like a real environment for it. So someday there'll be probably a Rust version of this virtual machine, and it's very small. Okay, so the idea is that like you can knock out an implementation of the virtual machine by itself in like a couple hours. It's an afternoon project. The toolkit is much more complicated. So like here, I'll show you. The virtual machine is actually, this is the BIOS. So here's the virtual machine is a handful of basically this. These are the main core operations of the virtual machine. So they have it's a stack machine, so you can put stuff on the data stack, you can pop stuff off the data stack. You can, if you want to add those two things together, well, you just take the sum of the top two things, right? So if you want to multiply, you take the product. Actually, you can actually say product here. Subtract, you pop one off, subtract the other, put it back on the stack. So that's the idea. And then there's a couple of like things for reading and writing memory, and then a couple for putting data on the stack from memory from the program itself, and then from these are all that, and then we've got hop if 0, jump, which is a long hop. So these are all control flow, call, return, and then next, which is this thing for it's like a counted loop kind of thing. And then that's it for the core machine. And then there's I/O, input output, for talking to some other system, the host system, right? And maybe if you had a bare metal version of this thing, it would I/O would just go right to the standard input and output. Or it could go to a console, who knows? Like say console, I mean like a richer text console with colors and whatnot, with escape codes and all. Anyway, I'm rambling a bit. Halts the machine, and and because it can work in this kind of calculator mode, right? The idea is that either you as the user or the host language, it doesn't have to be running all the time. So unlike a traditional computer where you turn it on and the instruction pointer starts moving, this kind of comes up in calculator mode where there is no instruction pointer unless you tell it to do something. And so the button, I call them buttons, but like it's sending a byte to a particular, calling a function, or if someday I hope to put this on an FPGA and you'll have a serial port, you'll send that byte to the serial port, and it'll pick it up and it'll come to life and do the thing it wants to do. And even you can have like many of these machines stuck together and they can talk to each other by sending these bytes. And so these bytes are instructions. The basic idea is that like these are kind of programmable instructions. The first 32. This is modeled on the ASCII character set, or actually UTF-8, right? So the first 32 bytes are things like Control M is the carriage return, Control J is the line feed. Control I is the tab character in ASCII, right? So if you're talking to a printer, like this was established years and years ago by people, all these little symbols mean something, but they're not really printable on the screen. Some of these have to do with like record separators, and this is the escape thing that allows you to do these fancy colors on a terminal emulator. Then you have all the printable characters, and then ASCII is a 7-bit character set, so that's it. This last one is the delete key, is a null character in ASCII, but it's emitted when you hit the delete key. Anyway, the idea is that these all things right here, what they do, if you send one of these characters, then it's going to invoke this operation, which can either be shown as it's 0, so it's in the disassembly it's shown as dots, so a pair of dots, which is the no op. But if you send it over the I/O port, the address in slot 0 is the address of a character handler. So if you quote unquote press the X button right here, then it's going to put whatever the ASCII code, whatever this number is, this byte is, onto the stack, and then it's going to run whatever this register is pointing to, right? So that's kind of the logic of this thing. You have these 32 buttons. They're all programmable. You can set these to whatever you want. So the first 32 times 4, like are registers in memory. You know, first 32 times 4 register slots in memory. I think I want to say 128. That can't be right. Yeah, double it would be 64, 128. The 128 bytes of memory are these registers, and that's the idea. That's the BIOS, right? So that is like the hardware BIOS, right? Is that you click this, it does something. You click this, it puts something on the stack. And then since ASCII doesn't have these, when you send one of these bytes, these are the registers. These are the operation, the core operations of the machine. There's like less than 32 of them. There's two rows would be 32, so this would be, I guess there's 28 of them at the moment. And so these are directly invocable. And those are your calculator buttons. If you want to put the number 0 on the stack, you actually have to hit load byte, hit 0. Okay, so that's how that works. And then it's meant to be extensible. So all these ones, these green ones, they're all meant for you to plug in something that you want to put in. So for this little implementation in Decker, I have a terminal device, which I guess I have a demo of it somewhere over here. Yeah, so I say hello, I run this. It runs all my little ASCII color codes that I plan to talk about. This is one of the first programming or first languages I ever invented when I was a kid, right? It would print out pretty colors based on one of these characters. And anyway, you can run here, and here's printing out a rainbow. I just rearrange those same colors to make it look a little different. Anyway, so I guess, and then just to finish up the thought, in UTF-8, if you click on UTF-8 here, it takes you to this Wikipedia page, and you can see that the way UTF-8 encoding works to get all these emojis and foreign language characters and whatnot is that it's a multi-byte encoding system, and so all of these characters say, okay, there are going to be two. Like C character C2 says they're going to be C, this column 2, right? So XC2 is going to say there are 2 more characters following this one. So when you see this character, expect 2 more. And then, these ones have 3 characters following, and they're all these characters, right? So these act as like escapes in UTF-8. And so I guess to summarize that real quickly, the way UTF-8 works is that any of these bytes, if you see them, they immediately mean that character, the corresponding character. So ASCII is just a 1-byte sequence. UTF-8 has these reserved as multi-byte sequences. And so you always start with one of these, and that tells you how many are coming. And it also puts some number, it starts like a number. And then the 2 digits following, or the 2 bytes following, add something to that number. And I'm not sure it's actually just adding the number. I think it's adding in, as if you were typing in like base 256, right? And it explains it all here anyway. But the idea is that in this encoding for UTF-8, all these are characters, and then all of these are never the first byte of a sequence. And so that's why they're reserved. The idea is that on this machine, it knows about UTF-8, and any UTF-8 sequence will put that corresponding number on the stack, right? So for you to process, and then immediately call this null character, whatever the first thing is, the character handler. So if you want to respond to a key press or respond to somebody sending you an emoji or whatever, it'll know what the code point of that emoji. It won't know what an emoji is, but it'll know what the code point is that it received, and then it'll run this thing so that you can do some kind of like parsing on it, or some kind of incremental response to that thing. So one of my intentions is to have like the editor, like a text editor, like on the screen, running in a tiny virtual machine. They're all tiny, right? So there are multiple of them. And so one of the virtual machines that just spins up at the start will be just connected to the terminal and respond directly to key presses. And so it will do all the the input buffering and whatnot. So you can hit Control H, which I guess is probably this one. No, this one. And then it's the backspace key. So when it receives that, I'll have to write a little piece of code that responds to backspace, and that will be the address of that code will be stored in this register. Then all these, rather than having one for each, sorry, all the control characters would be directly accessible by pressing Control and something on your keyboard, and you can do that. All these characters, when you press like the W or the Shift W or whatever, it will put that number on the stack and then invoke this one. So you have like two different ways of dispatch. And so when you hit Enter, that's actually depending on how your keyboard is set up, that's either going to be Control M or Control J, and it's going to invoke the carriage return or the line feed or whatever. And I might standardize that a little bit. Line feed. So this is Control J and this is Control M. Carriage return and line feed. Anyway, that's kind of the basic idea. I see people are watching, so hello. I hope I'm not rambling too much. These 2 bytes, for example, are not ever used by UTF-8 because they would be a way of the way it's set up. They would be used to encode one of these characters, so they're invalid. You always want to take it says something about the simplest pair or whatever, the simplest encoding, whatever. These would be like too big for UTF-8. So like Unicode stops here. These are not characters in Unicode, and so all of these are free. And so my thought is that okay, all of these are going to respond exactly as they do in Unicode. These, and then they will escape these things that if they had been the first item in the first byte in the sequence would have directly invoked some kind of internal thing. So yeah, that's the basic idea. And then the mapping is all of these are set up here. These starting at jump, these are all things that take that do something with the instruction pointer. And in calculator mode, there is no instruction pointer, so I'm thinking these might be overridable as well. Anyway, rambling. Okay, I didn't mean to go through all this. Anyway, today I'm working on a debugger. So I have a debugger for this in Pascal, one of the very first versions of this system that I wrote. If I say make run in the Pascal version, it fires up pre-Pascal. Oh, actually, it didn't because it's already compiled. It fires up make, and make knows that it's already done. So this is what the old version of the BIOS looks like. It's not pretty. It doesn't do anything. There's no, you can't really do much with it at all. But what it does is it lists the words, and then if you type the words, you can actually run that again. And then there is a bug, so this is probably going to be no, yes, it doesn't know what the word is anymore. Sometimes it remembers, sometimes it doesn't. The bug isn't in the part the bug is in some old code. Like I've changed a lot of things, and this isn't under test, so it broke. But there's also a debugger, and so if I hit the backtick key, and that said invoke the debugger, and we can see that this number in hex is on the stack. This is on the control stack, so this is the return address that I need to be returning to, or that it will eventually return to. And then this is the code of the BIOS here. Like me, this is more or less illegible, right? The white words mean call a function, so there actually is a function called b4 caret that prints that little prompt. TR, I believe anything starting with T is a terminal thing, so TR is read a key, duplicate that value. So this is actually not doing what I was talking about. This is not responding to button presses directly. This is actually reading a key from a terminal, from a console device. So it's not in calculator mode, and maybe it should be, but I hadn't had that concept yet when I wrote this code. Load a byte. So this is a space character. If it's equal, oh, I guess I can read this. Okay, so oh, I know exactly what this says. This says, yeah, so I just pressed the backtick key. And so what it says is, so read a key, wait for the key to press, duplicate the key on the stack, load the byte 60, and if it is equal to whatever that character is, which happens to be the backtick key, then hop if that's 0. Oh, if it's not. So if it's not equal to that, so hop if 0, then so if it is, oh sorry, if it's 0, then hop back -3 characters. That seems very strange, right? Hop 0, and this tells you how far to hop, and it says -3. That doesn't seem right at all. 1, 2, 3. It seems like it's wrong, but I guess it should be hopping back to the read key, right? To read the next key. No, I see what this is. This is not a negative sign. Yeah, this notation is confusing me. This is a 0. This is a leading 0. So hop forward 3. So if it's not equal to the 60, then or to 60, then see if it's equal to 20. So hop over all these 3 bytes, and then which is it did, or which it didn't, right? And then FE is invokes a debugger. That should actually say DB, but it's just not recognized as an opcode here for whatever reason in the disassembler. And then duplicate again the key. Sorry, no. This is weird. Basically, this said start the debugger, and then it didn't do anything else. It's just flowing into the next code, right? So that's the problem with assembly language. We can look this up, right? So if I say, I know I'm rambling here. This is this code right here. Here's the REPL. There you see EOL write byte. So B4, call B4. Not sure why you don't see write byte there. I don't know how to navigate anymore in this. I thought you used arrow keys. It's not working. We'll check in a minute. But anyway, this do is this do right here. Load byte 32. That's wow. That's weird. That's so wrong. This assembler, yeah, okay, so that's old school. This assembler is taking the number 32, and it should actually, everything should be in hex here. So this should be the number 20 like it is here in the disassembler. No wonder it's wrong. Okay, I don't know. That's something I need to mess with. Like I said, the Pascal assembler is really old code, and the BIOS assembler is really old code, and it's for like several versions back. So I don't expect this to work. Anyway, this is the old debugger. It's a mess. Maybe I should start by cleaning this up. Because my goal is to have the same BIOS code running on both Lil and, well, the terminal, or Lil and this system. Although Lil Decker does not have any concept of a read key, right? So I guess I could make this an actual keyboard, but you know, in here you actually type letters and it responds. Let me run that again. If I say words, like it's responding to each one of those letters. In Decker, there is no such concept of a key, of key press. Decker just does not provide that. It doesn't provide a keyboard event because Decker is meant to be used in a lot of different places. And basically, if you want to edit something on a touch device, it has this nice keyboard here. So you can't see the screen reacting to your stuff, and so there's just no. You know, it was important to the author of Decker to have parity here between the different ways of using the system, and to discourage you from making things that wouldn't be usable everywhere, right? So that's one of the constraints of Decker. So instead, you actually can, you know, what I do instead is I have a separate console here. I need to make this more easy to navigate. Term demo. Go. So here you actually have this. Whoops, I don't want that. Decker. You actually have this, and you can type in here and send messages to this, and have it, you know, respond on the text device or over here. Either way. So for example, if you say, oh yeah, I don't have it set up, but like I think if you say like emit a character. So this pushes the letter E on the stack, 65. Then you say IO. Oh, well, you'd have to push E again on the stack. So it'll print the letter E here. Okay, that's one thing. Interesting. I don't know why I printed a 0. Not intentional. Yeah, I think that was. I'm not sure. I'm not sure why that showed up there. And then if you want to print it over on this terminal, then you would say like X, and I think it is. I think it's also E, and then so whatever I did, I gave it a name up here. So this is E for emit, and yeah, so load byte, emit, and then call the terminal op. So load byte E, push the letter E onto the stack, and then run the terminal op, which pops this off the stack and says, oh, I want command E for this terminal. So this should put an X over here somewhere. And it did. See, it showed up right there. So that's the two different kinds of output. So if you look at the, wait, hang on, let me do it. Let me see if I can navigate this thing. I don't normally do it this way. Opcodes. I go here. Nope. I want the buttons. Where's the button? I think it's this. Yeah, this used to be just about the canvas. No, it's not this one. Bytecode is on. My point was, see, I added this terminal thing. So IO is like a built-in operation, I guess. And so the concept of an operation and a external virtual hardware device are kind of blended here, right? So these are internal operations. This is talking to an external hardware device, and you send it a 1-byte message. So, then it can say, okay, I'm going to pop something else off your stack or whatever. Yeah, I'm rambling about this. But okay, so going back to all this, as you can see, when I type words, like that's broken, right? So the BIOS is broken. I'm pretty sure it's broken because, you know, like I typed the word words here, it printed these words. Then I typed it again, it doesn't know the word words, right? So I'm pretty sure that something in the terminal code, this REPL code, is actually just broken. It's really old code. Things have changed out from underneath. Like I said, it's not under test. And so what I did is I started rewriting this BIOS with the intent of saying, okay, forget this terminal thing for now. Again, because the way I'm going to present it to people, the terminal here does not have an input device. It doesn't have a button you can press. So you can't do what it's saying down here where it's asking for a key, right? You can't. It should be called TE, but it's not. TR. So terminal read. You can't read a key in Decker. So so I have to do this thing on the side. And so my intent is in Decker, I'm going to do something where you type in words down here. I'll show you. Anyway, I rewrote the BIOS so that it's not dependent on this for input. And so what I've started with, kind of the story of the BIOS here is, actually there's a literate version of this, so let's go to that, bios.org. Thank you for listening to me ramble, by the way. I can't believe I don't know if I'm coherent at all. But I'm trying to retell this into a story that will be coherent in the future. And so the way it works is in this file, which is also on the GitHub under the BIOS directory. So basically everything above this line is like new thinking, modern stuff from my point of view, and everything below it, well, that's actually to do. These two are to do. They would be in that category. Everything below this line is old stuff below. And I guess the list of words actually would be part of the thing. Okay, so what the BIOS does right now, the way I think about it, one is that the quote-unquote buttons are part of the BIOS, right? Like the actual nature of the hardware is that you can send an operation at any point in time. And so if you give one character mnemonics to your functions, for example, this right here, this is wrapped as the mnemonic E. So this right here is actually invoking I guess it's A, B, C, D, E. So opcode 5, starting at 0. A is 1, B is 2, and so on. So E is 5. This is firing off opcode 5, which is has been assigned here, right? So I call it register E, right? So the assembler right here in this little window knows how to say, I'm going to, when it sees this, it says turn on the assembler, assemble the rest of the line, and then, but rather than giving it an internal name for a label, just set that register, set the E register. And so now, later, in the same like interactive session here, I can invoke that register there. And so in Forth, there's a language called Forth, which is very similar to this whole concept. There's a notion of a dictionary. You have two stacks in a dictionary, and your dictionary is full of words. And so at the assembly level here, at the machine code level, you have a dictionary consisting of those first 32 registers in memory. And you can assign them with the assembler, the interactive assembler, and then you can invoke them. And so my hope is at some point I'm going to have a video where, you know, the idea is that you start with whatever programming language you want, and you're going to make this virtual machine, right? That's like lesson 1 or lesson 0, right? And there's a set of test cases that cover that. And in the process of doing that, you have to, you know, it's a language neutral test suite, so you have to have some kind of input and output. And so you write like this little language, right? This little assembler language you're seeing here. And it is like a test harness that is directly controlling the virtual machine and communicating with the tests. And so it does very, very simple things. But my hope is that just by having these things, by the time you're done writing that program, the virtual machine and the little assembler and the, you know, that responds to it, the test harness, you have this thing that is now capable, that you could now use to interactively bootstrap like a real system. And so the things that you would be, you know, the next prompt in the test suite or whatever would be to build a BIOS, right? Because you don't want to name, you don't want to write code. I hate writing code like this. Like X is not a good name for a thing, but you only have, you know, the alphabet, right? You only have the alphabet characters. The names of the registers are the only things you can use to name a thing. This is not opcode, right? This is bytecode. I need to rename this, right? Whatever. But like these are your names, right? That's your dictionary. That's all you can do at the start, and that is unpleasant. And so what I think I'm going to do is probably have like a PDF you can download. It's like a memory assistant, so that as you're coding, you can fill in like what does each one of these registers do. Something that would look kind of visually like this, but you know, you'd have each like box for each one of these, but then you would write in what it does rather than writing in the number that's stored in it. The intent here is that this is going to be part of the, like, one of the next things you do is well, I don't know. I think I'm going to do a series of videos where I start out with using this machine and just programming it as if it's you know, it's an assembly language thing. And so I think the plan is that one of the exercises is going to be to make a little hex editor. Yeah, well, I didn't intend to start talking about that. But like once you get past that, you really want to like program in it, and even to use other languages, you know, to target this thing, which is, you know, where I'm going with this. You need some kind of BIOS so that all these things can talk to each other. So there's a global dictionary that's something more than these buttons, something more than just these, so that you have like named things. And of course, when you're assembling, like actually right even here, I can do this. I can give this a name, like execute. And if I run this, then over here, yeah, I just added this. Oh, you can't see it. So I switch in a little to this, and I can move this up here. So it says execute, and that just showed up because I typed because I gave it this thing. If I call this, like, you know, Fred, and I run this, then now I have Fred here. So this is listing all the things that I've defined. And my intent is that you click on this, and this little area, which is like a memory dump, will show that. So let me make my head tiny. So right now you can already kind of scroll through memory, and this is what's been assembled. So first, this is the start of memory, and you can see that these are the registers that have been assigned. So every 4 bytes is a register, and it looks like, so this would be A, B, C, D, and then E, and it looks like E is assigned to this. If I say what is E, what is the value of the E register? AF, okay. Well, that's really weird. I would expect it to be lined up here. Oh, no, I'm sorry, right. This is the E register. So 0, 1, 2, 3, this is the D register. I need like boxes around here so I can see this. This is the A register. So the number E is, in the way we write numbers, is 1AF. And so the number 1 is the operation, or the byte 1 is the operation control A, which is invoke that register, which is invoke the register right above this, which is empty right now, so it does nothing. And then AF is the address here. So 1AF is this is a 1, and this is AF, and this is little endian encoding. This is how numbers are stored on your, on almost every modern computer. So in memory, they're actually backwards. So yeah, I need something up here that shows this a little better. Anyway, so all these other registers are empty, and then after you get, or I guess actually I've defined several of them, and then when you get down to address 100, that's the end of the registers, not 100, 100, which is address 257, 256. Now this is the start of code. So this DC right here is the first item. I'm actually not sure why there's a space. It could be I have an off by 1 error in my assembler, because the very first thing you assemble should be that. So if I say like turn on the assembler and say A, then it should put an A right here. It did. Okay, so one of these is somehow incrementing something incorrectly, because the very first, like, the A should be right on top. Now it's over here. I don't know why. I don't know why that 0 is showing up there. Because these are not assembled. Fred is a label. This is just saying assign this, set the X register to the address that is currently being assembled, whereas Fred was set to the number 256. Where's X? X should also be 256. Okay, so it did not set the X register, and the problem is that that this version of the assembler went into assembly mode and didn't know how to recognize this. You should be able to do both. You should be able to give it a label and assign a register at the same time. And in fact, you should be able to do this, like a, whatever. You should be able to assign as many labels as you want to that thing in this table. I just haven't done that yet. Okay, so that's why. So now X should be, yeah. Now it's gone. It was assembling this as a 0 for whatever reason, and X is set correctly. Okay, so so in this BIOS, this code is actually, I've just taken the code from this file and stuck it in here. I'm kind of going back and forth here, and the idea is that what I've done is that the very first thing we want to do is that if you put an address of a function on the stack, then you need to be able to call that function, right? So that's another part of the BIOS, is if you just know the address of the function. So like in my assembler here, the lil assembler, I remembered as I made all these labels, right? It keeps this table of what those labels refer to. So like Fred right here is assigned to 100, and then a couple bytes later after these bytes, one is 100, 256, and then RI, which is read an integer. Well, that's 3 bytes later, and WI is, or our read byte is 3 bytes later, and then write integer, write byte, not 0 test, and that's at this address. So we just keep counting in hex, and it remembers that, and as a byproduct of that, I have this table in the lil assembler, right? And so now this is in my host language, and say I want to call RI, right? Well, so what would be a better one? I don't have an emit thing. But go ahead and put it. I should have this. So I call this emit here, and reassemble. This button right here is clearing the memory, reassembling everything. Actually, it's just running whatever's in here, but this symbol says clear the memory, reset the stacks, which probably ought to be one operation, and then run everything in this. We're running everything in here, and every line is just assembling something. And I took out all the comments and everything. I just shrunk it down so I could work with it a little better. So somewhere in here there should be the word emit now. Yeah, down here, and I see it's 1AF, right? So now as the host language, like as a script running in Decker, I could say so MB4 get VM. Actually, I think you can just say dput right now. Dput push to the data stack, and we can push the number 1AF, which is in Decker. There's no hex notations, but we say 1AF. No, sorry. We say parse 1AF, and then it'll push 1AF to here. So whatever that is, and then we have to say B4 step to. We can't do that. I have to. Yeah, there we go. You have to trigger the refresh of this thing. This is the data stack now contains the number 1AF. All right, now I want to execute that. And so we want to emit something, so we need to put a character to emit. So we'll call it X, or call it, I don't know, it doesn't matter what character, C. And then now we call X. And because this is actually not going to work. Let's run that again. Oh, sorry, I can't do it here. I don't edit it there. Edit it here. I got to get rid of that A because I added the stupid A in there. All right. So try that again, and then we'll push the number to the stack, which also we can just do by typing 1AF down over here. Anything, the assembler, this is an interactive assembler, it knows how to do that. So, and I take zap to remove ZP to zap it. Now I want to call that. Well, the way to do that is to push it to the control stack and then return. And then you can see now that the instruction pointer has moved to actually one character before that, because in a step, then the very next thing you do at the end of a step is increment the instruction pointer. So now I gave that process a name, so zap it, and then so yeah, that's right. And so what this does is it takes the number on the stack, pushes it to the control stack, and then returns, and that is as if you were returning from the function that was on the stack, and so it goes to that address. And so anyway, that's how exec works, and that is like, so this little 2-character thing is something that you could do that to from your host language to cause the virtual machine to start running at that address. But rather than giving it, two different operations, 2 different codes, we give it this name X, and so X is part of the BIOS, or Control X is part of the BIOS. All right, so that's it. I hope that made some kind of sense. The next thing, now that we can do that, let's find a way to, we want to make a dictionary and say, okay, I'm going to look up a word in the dictionary, and then once I find it, I'm going to execute it. And then it actually turns out that the way we do this is the dictionary has a structure to it. So it has a linked list. In fact, let's see, how would I show this? Well, well, I'll just finish this thought and I'll shovel into this. So it has three things in a row. So it has the linked list. So this is a 4-byte pointer to the previous entry in the dictionary. And then it has a counted string. And a counted string is a byte that says how long is the string. So it can be up to 256 characters or 255 characters. I guess it could be 256. And then and then that number of characters are used up by the name of the entry, so the key in the dictionary. And so then the what's called the execution token. Usually in Forth you have two things at this point. You have something that says how do I interpret the bytes that are in this thing, and then where do the bytes start? The value of the dictionary. So like it's kind of like a type code. I don't have the type code yet. And so the way everything is interpreted is you just call it and you run it as if they were virtual machine instructions. Probably at some point I'm going to add a thing that says how do you interpret these bytes? And so there'll be another field here. And so because I want that to be able to change, we have these accessors that says give me the entry name, give me the entry execution token, which is the start of the data or the code or whatever, like whatever's at that address or at that entry. So you're gonna follow the linked list, and you're gonna wind up with an entry, which is like the address of this top thing right here. So you're gonna wind up with the address of one of these, and then you want to say, well, I want to get the name, so I have to move 4 bytes forward because this takes up 4 bytes. So the name is just load the byte 4. Add it to the number that's already on the stack, and that's it. So that's you've taken that number that you have and you add 4. And this was this one now. Okay, you add 4 to get the name. Then you figure out how long the name is. So you duplicate that address, read the byte from there, which is the first byte of the string. It says how long it is, and then you add that to the address of the name. So take the name address, duplicate it, so you have 2 copies of that on the stack. From one of them, replace it with the length of the so read the byte, and then now you have the byte, you have the length and the address on the stack, add them together and return it. So these are the accessors for the 2 fields of the or the 2 other fields of the dictionary. Okay, so that's how it works, and then you have to make sure that your code follows that schema, right? You have to actually put this into memory somehow, and the assembler can help you with that a little bit. So again, this is kind of a literate program, and so the actual way that the dictionary is laid out is by following this, and all this stuff up to here is like the new code, and everything here is like ancient old stuff. So maybe we'll put a little comment here. Old stuff is below, or everything below is old. Everything below here is old. And in fact, at one point, there's a lot of stuff in here. We got terminal IO stuff, which is actually, I guess, duplicated somewhere else, or mentioned is compiled somewhere else. Whatever, doesn't matter. Anyway, a lot of stuff in here. So we got to start on the compiler, the Forth style compiler. We got printing numbers, and I'm not sure that word should be there. Whatever. And I think I don't even need these anymore. These were used to do the increment. Now there's actually an op that does increment. I never said this, but internally, these things for I/O, whenever you run these commands or whenever you receive these bytes, it puts that byte on the stack and calls the character handler. But internally, you're not doing I/O, so you have these are all free to do some kind of actual operation. And I didn't want to fill it up too much. And I came up with an idea so that reuses these registers. So each one of these registers, in addition to being able to just invoke it directly, which you can do from outside, like from the I/O interface, you can invoke them directly. But you can also internally, you can treat them as just variables, and you can these pairs of rows become methods on these. So like, so A here, control A executes register A. This fetches the value of register A, which is ironic because the symbol is the @ sign. And then down here, the symbol is the, in fact, I can do it like this. If I run this, right, we can see it. Yeah, so so now internally, the internal point of view of this is that this fetches the value of whatever's in that register, puts it on the stack. This takes whatever's on the stack and sticks it in that register. And this reads it just like this does, but it also increments it by a value that is either 1 or 4 based on a state. So I call it the value width. And I don't really like that. The idea was that sometimes you want to read a byte, sometimes you want to read a whole number, like a int32, and so that's 4 bytes. And so when you increment, you want to increment by 4, and sometimes you want to increment by 1. And so I currently have an opcode called RV, which is read value and write value. And as you saw, maybe saw it a minute ago in the assembly language in the BIOS, like one of the very first things I define is read integer and write integer, read byte, write byte, that sets that width and then calls read value. As much these used to be independent opcodes. I kind of think they should be opcodes, but then like when I do increment, do I want to, how do I know by how much to increment? And I'm now currently thinking that rather than just saying this is increment, instead what I should do is put a signed value on the stack, and then use that. So rather than incrementing by a fixed number, you just take whatever's off the stack and add it to the register, and that way you could put a -1 on the stack or whatever. You could put a 10 on the stack and do whatever you want. And so makes if you have a loop that's looping through an array or whatever, that means you have to run that load byte over and over again. But I don't know. I haven't decided about that. I'm still kind of going back and forth on it. Hi, Charles King. What language is this? As a JavaScript dev, I am seeing dust. So what you're seeing here is the assembly language. It's called B4A, so B4 assembly language for a virtual machine. This language right here is called Lil, and it is the scripting language of this program called Decker. So I've written many copies of the virtual machine. This virtual machine is written, or this version that we're looking at is written in Decker, or is written in Lil. I wrote in this language the virtual machine that understands this code. Yeah, that makes any sense at all. But yeah, it does look a little crazy. But yeah, so it's still up in the air. I may replace these with read byte and write byte, or read byte and read integer, write byte, write integer. I don't know. I haven't really decided yet. I've also thought about maybe having an array that associates a size with each one of these, and then when you do this, it'll just increment it. I don't know yet. But the intent is that you have like the core of a virtual machine that does a lot of interesting stuff, but it's also flexible enough that you can override big chunks of it. Like all of these are opcodes that you can plug in yourself, and all of these are opcodes that you can plug in yourself. The difference being that these would be directly accessible from the IO, right? Like you could just send 1 byte to trigger this, whereas these, or like over a network or something. Whereas these would be something that you could only refer to internally. Right. Anyway, otherwise, when you're doing I/O operations, these, as I said, are part of the UTF-8 encoding, and so they say read the next couple bytes and then build a code point. Yeah. Okay, so. I keep asking, what is this? This is a virtual machine. We're doing the BIOS of a virtual machine. I guess I should have some explanatory text here. What I'm trying to do, what I want to do, is I want to be able to, I was going to show this. All right, so what we're looking at here, each of these, you have a virtual machine. We're going to do the assembler. So you are creating a virtual machine like one that an OS can be loaded on top of. So the word virtual machine, we use that, yes, but it's not. Like if you run Docker or whatever, I don't know, I think that's a container, not a virtual machine. But if you run like VMware, right, that's a virtual machine that is a virtual x86 computer, right? And so it runs an x86 operating system. This is not an x86 computer; it's a B4 computer, so it's just something I made up. And the picture I keep showing is what I just do. Sorry, I hit the wrong key. This is the bytecode. So this is these are the assembly language instructions for this computer, the B4 virtual machine. And then I have multiple implementations of it. One of them is written in Pascal and has this quote unquote nice interface in the terminal here, where you can type in a word and it's supposed to do something, but it's broken, it's buggy. I've broken it and didn't have it under test. But in theory, you can run a word and then somehow it gets screwed up. So the word by ends the system. And it could have an operating system, but in practice, this is meant to be a tool you can use to like script your programming language, or it's kind of three things. There's three goals here. One, eventually I'm going to make some videos that are much more organized than this, that are going to be explaining how the system works and how to program from scratch from like an assembly language. And I wanted to provide an assembly language that I thought would be fun to use and nice for like building a whole system from scratch. That's one. Two, the second goal is to provide, I use a lot of different programming languages, and the goal is to have a toolkit that I can take from language to language. So if the first thing I do when learning a new language is implement this virtual machine, suddenly I have access to all the code that runs on that virtual machine. And so I'll have there's going to be a directory called kit that just contains like parsing code and like a little editor and things like that put stuff on the screen and give me a toolkit that I'm used to, so I don't have to learn everything from scratch, or other people don't have to learn everything. I guess goal number 3 is to make a virtual machine that is customizable, which is why most of these ops do nothing by default, so that you can plug in your own as an application developer. And so you have the virtual machine either written in your language or bounded to your language through dynamically loading a library. And so now you can run this code and that's running on the virtual machine, but you want to be able to extend it with things in your application. So for example, well, like right now, this terminal and this the terminal, which is here, which I don't know if you were here, I demonstrated this earlier. I can't tell who's watching, right? I just see a number. This code right here is printing out, something on a terminal. Well, that terminal, this little terminal here, is just something I made up for this application, right? For this demo purposes. It's only got 16 colors because little Decker only gives you 16 colors. And so that's like not a general purpose thing. It's not part of the spec for this thing. It's just something I'm adding to it. And so that terminal is actually treated as if it's an opcode. I just added an opcode that says take a letter off the stack and then use it to call one of these functions, like clear the screen or put a character here, or get the move the cursor to a certain place or something like that. Probably should be one to turn the cursor on, turn the cursor off, that kind of thing. Right. So in the old school, I had it's putting a terminal here, and when it does that, rather than drawing pixels to a buffer like it does here, so here when I put a character on the screen, I actually have to draw a picture of the character. Like there's actually there's a font on one of these cards. So there's internally there's this canvas right here. This is a canvas that shows that shows the alphabet, which is actually the old VGA thing. So it parses this data, it loads this font, and now as I move, it's copying, you know, one little character from each from this thing. It's copying a slice of this, and it's going to put it over here. And if I run this, this is my favorite little demo. You know, it's copying, you know, characters over and over again and coloring them in different ways, and that's what the logic of drawing a character on the screen means in Decker, right? Because that's what I have to work with as a canvas, and so on. Whereas here, this is this program is called Putty, and then inside of that, I'm running a program called Team. I'm connecting over secure shell to a Linux machine. I've got Tmux down here that is like controlling my my interaction with the Linux shell. Over here, I've got Emacs running, and here I've just got, I guess this is Bash. And so I'm in both Tmux and Putty are terminal emulators for old school VT100 terminals that have color, right? And the way that works is that you actually print a character to them that says make things red or make things cyan or make things, you know, whatever, and change the color. In fact, even this prompt, if I say echo PS1, right, in Bash, right, this is the escape character, backslash, or it's actually the control open bracket, right, is the escape character. And, you know, over here, that would be, where to go? I need a better navigation for this stuff. Would be that. I'll be waiting for the videos. Thank you. Yeah, please. It would be much more comprehensible then. But yeah, so to put a color on the screen in this terminal, you have to emit this escape code. I'm not sure what this /33 is. /03, I don't know what that is. It's the backslash open bracket, which is the color. What's a null character? That's weird. I don't know what that's doing. But this 3301, this is saying like 01. I think, if I recall correctly, it's been a while. I think it resets the colors to, like, you know, the default gray on white. Actually, that's what 0M does. I don't know. But anyway, you can see this string right here is causing it to print in these colors. And usually, if you have a Linux machine, you just type echo PS1, you can see what the codes are, and then you can see what it's doing. Yeah, that's enough of that. But the point of that is that I couldn't use the same code to the terminal, right? It wouldn't be the same, right? Because here you're dealing with pixels, and over here you're dealing with escape codes, and so there's different implementations of what a terminal is, depending on the environment you're living in. Like if I'm in a game engine, I probably have to draw something on the screen as well. And you know, there's a Godot version of this virtual machine as well. And the intent is that, like, all the basic stuff runs the same on all these on platforms, but, like, you know, all these tech stacks. So you can run it in JavaScript. You can in a browser. You can run it in Decker. You can run it in the terminal here. All these things will run, and you'll have the same code. But then some of the things you have to plug in yourself to customize it, or you plug it in because you want to, like, again, if you're in a game engine, you want your game to do things, and you want to script the way that things happen in the game. And so you could add your own opcodes that say, like, you know, have an opcode that shoots the gun or something, like, you know, steers your character, or, you know, quits the level or pauses or something like that, whatever you want to do. Or like if you want to script somebody going back and forth, you could say, well, flip the sprite to this sprite or something like that. And these would all be just things that you add to the virtual machine as you implement it. So it's like a framework for building virtual machines. Yeah, and then so then put all that together, and then you have something that hopefully people are interested in learning to use for themselves. They go through the process, they fully understand this thing, and I like how Dev's minds are just curious. Yours is brilliant. Well, thank you. I appreciate that. I've been working on this for a long time. It's something I've been wanting to do for ages and ages. So I'm taking the time to do it. Anyway, it's not that brilliant because it doesn't work. So as I was showing, I have a bug here. This is running in the Pascal version. So I just typed words. It knew what it meant. It looked through this list of words and it found the word words and it figured out what it meant and it worked just fine. Executed it. Now I have words. It doesn't know what the word is. So there's some state that's getting screwed up. And I think it's because like I've changed the nature of the virtual machine a couple times and didn't have this stuff under test. So I'm trying to get, it's still not under test, but I'm trying to get this part of it working on both machines, on both the Pascal version and the Lil version, and the Lil version is not working. So let me go back to this. I appreciate all the questions. But I sat down to write some code here, and I'm just talking about it. That's okay. So when I hit that button, it clears memory. This clears the memory. This resets the stacks. These stacks here. This does all the definitions. So I've defined all this junk. And oh, okay. I actually have to explain this. So refresh. What the assembler does is when it encounters a word like this, it starts with a colon. It says I'm going to create a table. I'm going to add this to a table that looks like this table right here, in memory. And there's a version of this in Pascal, a version of this in Lil, and so they're both doing the same thing. And I just happen to be showing the table on the screen here in Decker, Lil, and it's associating these labels with an address in the virtual machine's memory. And so it starts at 0. It starts at 0 and just lays down code in memory, right? Actually, I'm sorry, it actually starts after the registers. So the registers contain the first 256 bytes contain are just blank at the start, and then as we go along, we're going to fill them in. So when I say colon Q, you notice that's not in this table. What that actually does, even the very first thing, the first entry here is RI, whereas the first entry here is X, and because it's a one character uppercase ASCII thing, it's actually going to stick it in wherever X is in these first bytes. So somewhere in here, this is the word X, or the X. In fact, if I delete all this and I just hit enter, I'm expecting all that to be blank. Oh no, I think there's right, because these are internal registers now. So everything above 8 is an internal register. This is X, and then this is the backslash register, control backslash, which is what you run out. There's only 26 characters, but you have 36 or 32. There's only 26 letters in the English alphabet. There's 32 control characters, and so some of them have punctuation marks. Like that's the @ sign, and then at the end it's like open bracket backslash close bracket caret, the control this thing, this thing, and then underscore. And so I try to give weird names or meanings to the underscore ones so that you can use the letter ones for your own use. And what the backslash does is it's a way to say when you go out of calculator mode and you start executing, where should you start? And you don't want to start at 0 because these are all registers, and so they can contain any numbers. You don't want to execute arbitrary numbers because who knows what they should be. So you always start at 100, which you start at address 100, which is byte 256, and in hexadecimal, that's 1 0 0. So this right here is the 0, this right here is the 0, and this is the 1. Because it's written in in memory. It's stored in little endian format. So this is register X right here. I really need some like labels on this thing. This is register X, and this is the 0, and this is the 1 for the number 1 0 0. I'm sorry, this is register X, and that's because I started compiling at the start of memory, and this is register / because it's this is where memory should, or this is where execution should start. And so this is a DC whatever. I screwed it up, didn't I? C R, I said X, and then we have to say what X is, and that is push the data to the control stack and then return. Yeah, and that's, hopefully I didn't screw that up. Okay. Anyway, so yeah, so I guess that's really all I had to say about that. So now I've populated some other things. So like I defined F here, so one of these is F, and I can't really tell what they are. I need a better visual system for that. In fact, I have that. The intent is that in addition to this thing, you're going to have this little guy over here on the screen, only for the little version, and you'll be able to like see what the content is of all these registers. What editor is this? This scripts debug test. This right here, what you're looking at is this program called debugger. And if you go to this address, beyond loom debugger, I'll paste it in the beyondloom.com debugger. You can get this for yourself. Did it send? Yeah. It's free software. It's kind of like HyperCard. I showed this earlier, but if you go, the reason I'm using debugger, part of it is the person who wrote it is a friend of mine, and I like it. But also, eventually I'll be able to upload this. So if you go to this address, this is not ready to go. This is not exactly the same version you're seeing on my screen. But this you can run this in your browser, and you can come right here and just like type in things like you say 22. There you go. 22 are on it's on the data stack, and then you say 80 for add. Well, it added them and got 4. So the idea is that you can even download this debugger. You say file, save as, and you can save this. If you save this to .html, you can save this whole HTML file to your hard drive, and now you just have this thing running. So that debugger provides that, and it's just such a nice little tool for like shipping a demo of something that I wanted to make my thing run on top of debugger. On the other hand, it does have some constraints, like you can't you can't type into this terminal. You only have 16 colors and things like that. But that's it. So but it does have this. Like this is a oh, how do I do it? I don't have a. I'm used to pressing F2, but I guess that doesn't work here. But if you go to Tool, Widgets, all right. Well, this is a thing. This is a widget that I made in debugger. That is like my own extension to debugger, and you can you double click on it in widget mode. You can go to the prototype, and you can like see see how it's built and how it's just really cool. It's a extensible. He calls it a multimedia sketchpad. It's a modern day HyperCard clone, and I really like using it. So I thought I would build my stuff on top of this so that it had that property that you could download it and take it lots of different places. For actual work, you probably want to stick this like in your JavaScript application or your C application or your Python application. And so there's other implementations of the virtual machine, but this one is just particularly nice for situations like this where somebody shows up and says, "Hey, I want to try this." We just give them a link, and now they can try it right there in their browser. So I really like that. It's also got debugger itself is just a really cool thing by itself. If you say file new card, I'm not going to do too much of this, but if you say debugger toolbars, right? You can just draw. Get a pencil here. You can just draw. You can draw here, and then if you don't want it, if you want some color, you can put colors. It doesn't actually come with these colors. These are custom colors. You can do all this stuff, and then now you've got you got a little system. You can start making things whatever you want. All right, but I'm going to get rid of this. All right. Anyway, I'm rambling. Okay. So I'm still trying to get to the problem I'm trying to solve. I haven't gotten to that point yet, but it's kind of actually good to talk this out. Oh, I wanted to say this. So this little symbol right here is a macro. The dot caret is a macro in the assembler. The assembler comes with like several predefined macros for like structured programming. So we've got if, then, else, and things like that. Although they're postfix, so it's like you say what you want to say, and you say if, and then else, then, whatever. But this macro right here, dot caret, what it does is it looks, again, caret is one of the ASCII control characters. So control caret is a, if you press control caret, it does something special on your keyboard. And presumably it did something for a printer or a device that was being controlled by bytes or whatever. But what it does on this virtual machine is, well, it can do whatever you want. But what I'm using it for is I'm using that register to store the tail end of a linked list, right? So let's go back here. So the register is called caret, and if I run it, it puts the @ sign says give me the value of that thing. So it put the number 19E on the stack. I can also do this to just print it out. And this tells me, okay, at that address. So if I go to 19E, this would be way down here. 1C, and this is not a very good debugger, right? The intent is to make a good debugger. 19. So then under E, it would be this. So the caret register is pointing at this spot in memory right here. And this looks like code, but it is actually not code. It should not be code. What it should be is the 4 bytes starting here, 1, 2, 3, 4, actually really looks like it. What it should be is that it should be pointing at an address here. 19E. It should be pointing at the last definition, which is these are defining registers. So it should be pointing at this word emit. So if I say emit, it's 1AE. Did it find something after that? Oh no, sorry. It's pointing at here, the word exec. It should be no. Yeah. Yeah, this should be pointing at exec. But it's not. We should see the word exec here. Is there another? Did I miss one? I'm looking for that symbol. So this symbol right here, the purpose of this symbol, this turns on the assembler. On every line you're in execution mode. So this turns on the assembler, so you're in assemble mode. This symbol right here should say take whatever's in this in the caret register, pointer register, write it here, write it to memory, assemble it, like assemble that number, and then update it with a pointer to the number you just assembled. It's possible that the little assembler, that the assembler I have here is wrong, because this seems wrong. I would expect this to be pointing exactly at this point, and so so that if I looked at this number, 19E, and I went to that address, 19E. Oh, maybe I did. Maybe it is right. Maybe I just missed. I lost track of what line I was on. I thought it was pointing here. No, it's here. Okay. 19E. One, two, three, four. Okay, yeah. So this number right here, 1, 2, 3, 4. So there are 4 bytes in memory. This number, this number, this number, and this number that are the content of this register. So, which should be the numbers 19E, right? It doesn't make any sense. I'm a little. This is not set up for explaining, right? I'm talking about how it should work, and like this is not working, right? So I want to debug this, right? This is what I'm trying to do. Anyway, the point is, what it's supposed to do is that this number basically it puts a number down, and then the number is the address of this number, right? So as it goes along, it keeps track of the last place it put the number, and it makes a linked list. So here, this is pointing at whatever the last number was, which is this one right here. So the number fine. So the word should be in the dictionary. If I were to type the word, if I were to iterate through the dictionary, the last one I should see is exec, and then s equal, or s seq, and then find, and then ext, and then ename, and there are extra ones here, but and actually it actually does. Okay, well, first of all, I edited it, and second of all, I put it in a different order, and they're going to come backwards. What it actually does, it should say, sorry, yeah, so exec, so we have exec, and then that points to s equal, because of this here, and then s equal points to find, because of this here. And then this here, it points to ext, but I actually removed dec and inc because I don't need them here. And this points to, anyway, it makes a chain. And so that's what this little symbol does. And the result of that, after you've done the assembly, the result of that is actually stored in the caret register. It's not supposed to blow your mind, right? This is supposed to be, I mean, this is hard stuff, right? And I didn't figure this out. This is stuff that the people who there's a language called Forth that perfected this years and years and years ago, and this is kind of a scaled down version of that. But I mean, this is what a linked list is, right? It's a linked list. It's a pointer to the previous thing in the list, right? And when you start, the pointer goes to 0, so 0 is your null pointer, right? So the very first thing here, it should be a bunch of zeros at address 100. No, sorry. Here it should be 0. So we should see 4 because okay, so that's a distinction I didn't make. This is a label inside the assembler. But that's as soon as the assembler is done, like this gets thrown away. So how do you keep the memory so that it knows the names of things? So this is not exposed. This does not have a name in the dictionary. RI does not have a name. RB does not have a name. They have a name in the internal label dictionary, but then that can get blown away at any point. But here, I'm actually writing a number. So right after the word NZ, so NZ is at 10E, 10E. So if I go to 10E, and over here I see LB 0 equal not. Load byte 0 equal not return. Then the next line is this. Oh, this is totally wrong. Yeah, look at that. So I have a bug here, and this is actually the bug I was looking for. But now I see what it is. So if you notice, this is issuing. This is issuing that this is a part of development I never thought existed. Yeah. This is exactly why I'm making this course, right? I want to make a course about this because when I started programming many years ago, even in Pascal, you could drop down into the assembler. You could look at memory. If you wanted to put a character on the screen, you wrote directly to computer memory. And over the years, like this is not good, right? It's not fun. This sucks. It sucks to be this low level, right? It sucks to write in assembly language, and so nobody wants to do it. And so all these tools are made to make it pleasant to write programs, right? So you have Python and JavaScript and so on that abstract all this away from you. And it's so much nicer to use those high-level languages. But the problem is that a lot of people, when they start learning now, they naturally learn the tools that people, that people actually use, JavaScript, Python, even Rust or whatever, and you don't see this stuff. You never get exposed to this stuff as a student, or even learning on your own, because who would want to, right? But I feel like, and so, some people, they start working on these things and they do just fine, right? But a lot of students of programming feel like they can make the computer do some things, but they don't really understand what's going on because they never experience the low level stuff that's being abstracted away. So okay, no, the word assembler means, so the question is, so the assembler is like an object in JavaScript where there is a key and a value. No, that is called a dictionary. And so what I'm constructing in memory is a dictionary. So I'm trying to, I'm doing what JavaScript is doing when it makes a dictionary, right? So somewhere in JavaScript, you can't see this, but there's physical memory on your computer, and JavaScript has access to it. And so when you put a list of items in JavaScript, well, I don't know that it actually contains a linked list, or even a dictionary contains a linked list, because they probably use arrays for this. Because like one thing you don't have here yet, that I'm working my way up to, is like being able to allocate a slice of memory and then later garbage collect it, right? I can't do that yet. I have to just start at the start of memory and put things down in order. And so that's what I'm doing here. And so so my dictionary is made with a linked list. Probably later on, you'll make in the course we'll make arrays, right? And so then you can allocate a chunk of memory, put whatever you want in it. That's a much better way of doing most data structures, right? But linked lists are simple because you can start anywhere, and you only need one cell of memory. And so what the memory is like in this machine from a JavaScript point of view, like there actually is a JavaScript implementation of this machine, and I believe what I did for the memory there, I'll pull it up, from a JavaScript point of view. Where's my browser? Oh, here, because I'm thinking this is little, but it's not. So if I go to GitHub Tangent Storm v4, and somewhere in here at the top there's JS for JavaScript, and then we have this. Yeah, this. So B4 is the virtual machine, and B4i is the interpreter. But inside of this, we should have like all these opcodes, and we have an array of opcodes. And then when it says what is memory, well, it's just an array, a JavaScript array. Sorry, that's the stack. This is RAM. The RAM is a uint8 array, so it's an array of bytes. And in that particular one, I just made it 4 kilobytes, and fill it with zeros. And so then you treat this very much like an array in Java. It is an array. It's one of the typed arrays of it shouldn't be, oh yeah, uint8 array. Uint8 is a byte. So unsigned int 8. So an 8-bit integer is unsigned 8-bit integer array. And then it's, yeah. And then there's like some tools for like reading 4 at a time. Although really what I should do is just make a slice of that treats it as 4 bytes at a time. Anyway. So then the assembler is the thing that says the assembly language is this. Like, so this is a word in the assembly language. DC for take something from the data stack and push it to the control stack. So there's that number up there. And if I say DC, it goes over there. And if I say CD, that goes the other way. You see it moved up and down here. And so the data stack is where you put in JavaScript you have parameters to a function, right? And then you're going to do stuff, and then you say return, right? So the parameters go on this in this system of the world. The parameters go on this thing called the data stack. There's no actual syntax for it, but like that's where you put your parameters, is on the data stack. So again, when you say to add, add is a function that takes 2 arguments. This is like the plus sign, right? We'll say 2, 3, and then you get a 5. 2, 3, and you'll get a 5. When we add those together, we get a 5, right? So it took, if I just say 2, 3, we have the numbers 2 and 3 on the stack, and it's a stack. See, the 5 was already there, and I added a 2 and I added a 3. And if I do it again, there's more of them, right? So it's a stack. And then when I say add, it takes 2 numbers off the stack and adds them, right? If I say zap, it removes something from the stack. If I say multiply, ML, it multiplies 2 by 3 and gets 6. If I say sub, it should give me -1, right? Because 5 minus 6 is -1. So that's the concept of the stack. And then the control stack is saying, right, where do I go back to when I say return? And that's what I see everyone left. So but that's what the control stack is for. And normally those are intermixed. Like in the C world or whatever, Pascal or C or in most languages today, you have basically the control stack contains all the data, right? And so all the arguments are on the control stack, and that's why you have to have names. You have to have named arguments because they're going to be in a particular position on the control stack. Whereas in this kind of language, you just have the stack and you don't have to have any arguments because the stack is the argument list, and you just change it as you go along. Okay, well, everyone who was watching live is gone, so no problem. But I still have a stream to do, so I usually I'm more used to talking to an empty room. And let's see, I have about an hour and a half left. I'm gonna have to go in about 90 minutes because I have to go get a little girl from a bus stop. Okay, so hopefully in that time I'll be able to figure something out here. All right, so anyway, I guess the distinction I wanted to make for those who are still watching on YouTube or on in the future is that these are assembler labels, and this is the oh you're back. Okay, now it says I have 2 viewers here, so welcome back. Or sorry it said you were gone, whatever. Anyway, so the idea here is that I'm manually constructing this dictionary. So the assembler, the question was, is the assembler a dictionary? No, the assembler is the thing that translates each one of these little things. It translates the assembly code to bytes. And so here, nothing gets translated, but it keeps a label. But in here, when it sees this, all right, so we're starting it, we cleared everything. So here, the very first word in memory, starting at after the registers, starting at 0.100 or 100, is DC. So it took DC and it put this byte down here. What is DC? I don't know. If I wanted to find out what that number actually was, I would say the values are bytes, and then I would say 100 or 100, 256. This is all hex, and then read a value, and it puts that on the stack. So that is the number 90. So 9 times 16 plus 9 times 16, whatever that is. That's what this number actually is. But the disassembler here is showing it as DC because the assembler, right? I didn't want you to have to know that that's the number 90 in hex, right? And so as far as it's concerned, this is just DC, and it's just some byte, and RT is a byte. So the assembler took this. The assembler ran this code right here, or looked at this code, and it said, okay, I'm gonna assign. It sees this and it says I'm going to assign the X register. It's got like an empty virtual machine in front of it, right? It's got registers, it's got RAM in that virtual machine, and now the assembler is going to put stuff into the RAM of that virtual machine. And so it says, okay, register X is the, if you look at memory, register. Let me load this up, and then I can switch back and forth between this. If you look at the byte code, so I drew stuff on here. If you look at this, and if you imagine memory is laid out like this, and these are every 4 bytes, then what this line of code does, :X, it says I'm going to put a value right here. So I'm going to associate this register with the address right here, right? Because there's 32 registers, and then there's RAM, there's extra RAM that you can put whatever you want in. The first 256 bytes, which are these 32 registers, they're special. They're a dictionary. They're one kind of dictionary. And this kind of dictionary is the keys are the @ sign, A, B, C, D, E, F, G, all the way to Z, and then this character, this character, this character, this character, and this character. And every one of those characters is mapped to a 4-byte number, right? And then when you invoke this as an opcode in the virtual machine, whatever this number is, what it does is it looks at this register and runs that code, runs that as if you called that function. So that's what we're doing here. We're saying I want to be able to press so now forget that this is memory. This is now a keypad on like the front of the machine. When I press this button, I want this code to run, right? And it does that by associating in memory, a particular slot in memory is assigned to that button, and so on, right? So you click that button, it runs that code, and so that's what happens when I press here. You know, we don't have the button in front of us, so the magic code to make that work is this. This is like describing press that button, run this code, and so it's a 1-character code, and so that part of the dictionary is like always there, and so we don't have to keep track of where they are. We just look in memory to see that, and so that's why X is not here. It's actually in memory, whereas here this is not stored in memory. This is stored in an array in the Lil programming language, which is what is inside of Decker. So this is all stored in Decker, and then the address here is stored in. Now this address should be 0, right? Because it's the very first thing. Sorry, it should be 100. So if we type $X, the assembler should tell us what's in that register, and it is. That's the number 256. And if we look in RAM, and again, whatever X is. So if we type I don't know how to do this. I don't know how to map back to that number. Because what you should be able to say this. Maybe you can say this. Maybe you can say this. Let's see if it works. No, it crashed. Okay. Yeah, because this tried to run it, and then this doesn't work yet. I don't have a good way to put that number on the stack. Do I do it like this? I do. Okay, that's it. Backtick is put the number on the 6. Whatever this hex number, if I look at that, if I do this, it shows me the RAM there, right? And again, it's little endian. So the first 4 bytes of the first 4 bytes of this string are the value of X. So we know the value. I looked here and it told me in hexadecimal what the number is. Now I said, okay, what is X? And it said it's drawing it in hex for me here. So that's the control character. That's the address of this register. I'm sorry. Backtick X is the address of this register, and it's not an opcode. It's just like it's like a special syntax in the assembler. All right. So now that I know what that number is, like ideally you should be able to see what this. You should get this memory dump as soon as you type this. It should show you this, and then show you this, but it doesn't. So I'm doing it manually. But when I look at that address, the first 4 bytes are the value of X, which is this 100 right here. So, all right, these 4 bytes. So dot means 0. Control A, well, that's the that's byte. You know, in the byte code, that is the symbol for bytecode 1, right? Bytecode 0 is this. Bytecode 1 is this, right? And so we have in memory 0, 1, 0, 0. But actually, but in hex, like this 0, 0 right here is this right here. This 0, 1 right here is this right here. So instead of drawing 0, 1, it's drawing Control A. Instead of drawing 0, 0, it's drawing dot dot, and then this dot dot is this 0, 0. Oh, sorry, this 0, 0, and then the next one is this 0, 0. Right, and then there's a bunch of zeros after it, because it's little endian. That's just how bytes are arranged in memory. Okay, the point of that was, okay, so that's what this does. Now with RI, this is like an internal name. So this is like X is now, even though it's only one character and it's a terrible interface, that is a user interface for you to now use this machine to execute this. And the point is, again, if you missed it, is that we're going to put an address on the stack. We're going to push it to the control stack, and then we're going to call return. And so return says, go back to the address that's on the stack, right? Remember, when you call a function in any language, you have to remember where you were. The computer remembers where you were, calls the function, and then the function says return, and then you jump back. So the way it knows that, and remember, you could be many levels deep in lots of different functions. And so the way it remembers that is it stores the instruction pointer in memory on the stack, right? In C and Java, there's one stack called the stack. And here we call that the control stack. There's two stacks. The fourth-like languages have two stacks. This is a fourth-like language. And so, yeah, so that's what this does. We're gonna take a number off the stack, push it to the control stack, and then return. And so then, instead of going back to whatever function called, whatever code called this control X, what it's actually going to do is just jump. We're tricking it. We're tricking it into thinking, hey, you need to, instead of returning to wherever you called from, just go to an arbitrary address. So this is like a go-to. I don't know, it's called call with current continuation in Scheme, but I think it's a crazy name when it's just these two characters. I'll probably do a whole lesson on just this because it's such a crazy concept, and it makes so much more sense if you could see it in a debugger, but I don't have a debugger because that's what the point of this was. Anyway, so because the name of this is a register, it stores the value 0, 1 here. Or sorry. RAM is, you got, I have a picture of this. A picture of what I'm talking about. Let me find it. Oh, I don't have a picture. It's not in this one. Oh, it is. It is. It's just they're out of order. All right, so RAM is divided into different chunks, and each one of these bytes right here or each one of these boxes here is 256 bytes. So the first part of RAM here is the registers. And that's actually, so it's saying 00 through 0FF. So the first 32 registers, the ones I talked about, there's an additional 32 registers that are kind of private and internal, like the instruction pointer and the height of the stack and like internal information about the virtual machine itself, so you can inspect yourself. And so that's there. And then we start at what, is that right? 32 times 4 is not 256. That's completely wrong. Yeah, okay. Yeah, so really what you should see here is this should be half. These two things should be merged together, right? Because it's 32 takes up half of this box, and then the other private registers take up the other half of this box. And then we immediately start, you have code to start working with stuff. And then eventually there's going to be like a reserved area in memory for input and output. All right, so this picture is useless because it's wrong. I didn't even know that, sorry. Okay, well, anyway, but the point is that the part that is right is that the first 256 bytes are reserved for all the registers. There's 64 of them, not 32. 32 of them are the ones that you can use, and then there's 64, or then there's another 32 that are internal that you don't get to know about, but they're stored in memory, so that you can store and restore the entire state of the machine. Okay, why was I saying all that? Oh, because then when the assembler starts, it can't, you don't want to corrupt those registers, so you have to start right after that. And so when you start by default, you should expect to, if you don't tell it to do something else, that if you just start the machine and tell it to go, then it's going to run starting at address 256, right? So which is this number in hex. So when you start the assembler and you tell it to store the current assembly, we call it the here pointer, the HERE, the pointer that we're looking at right now, here, store this here in in the X address. So that's why X is 256.100. All right, so now we've emitted 2 bytes, and then now RI, now, okay, so it sees that, that's what that does. It sees DC and it says, okay, DC is an opcode. I have some table that tells me what all the opcodes are. So I'm going to take DC and stick it into memory at this address. There it is, boom. RT is the return opcode. So it sees that and it's going to stick that there, boom. All right, now that we got to the end of the line, we're back in direct interaction mode. And then this puts it back in the assembler. So now the assembler says, not only go into the assembler, but also create a label here. There you go. And we've emitted 2 bytes. So now we're at 102. And now we're going to emit this byte. This is an opcode. It says values are, so we're defining a function here called RI, which is read integer. It says values are integers, as in rather than bytes. This is an opcode. Read a value, so read one of those integers, and then return. And so that's what this whole thing does, and that's 3 bytes. So you can see that when we get to the next one, it's incremented by 3. So we went from 02 to 03, which is, when we make this label. And we have another 3. This says values are bytes, read a value, so read a byte. Here it says values are integers, write a value to memory. So it's going to take some address off the stack and then write that. So the top thing on the stack will be an address. The thing underneath it will be the byte you want to write, and it'll write that byte to memory, and so on. And then when we get to NZ, this says load a byte, and then so that's an instruction that says, where are we at? Right here, load a byte, and then where do you load it from? You load it from the next address. So load this byte, which is a 0. And so that puts a 0 on the stack. And then EQ is, right, hang on. Let me say that again. The assembler is the program that is taking these 2-character symbols and turning them into bytes and sticking them into memory. That's what the assembler does. And then at runtime, we're running those instructions. And so at runtime, that's what LB0 puts a 0 on the stack. At instruction time, LB0 puts the code for LB into memory, and then it puts the 0 into memory, which we're seeing right here. And then EQ is the assembler is putting that into memory, and then the NT, the assembler is putting that in memory. So equal not, so this says not equal. Basically, this whole thing says not equal to 0. This whole expression, 0 equal not, is I'm giving it the abbreviation not NZ question mark for not equal to 0. And it's a function, so you have to return from the function. That's what that is. Okay, this line right here is a colon and colon. It's also starting the assembler, because as soon as we hit a new line, this goes back into interactive mode. This B4I is B4 interpreter or whatever. So you can directly interpret the byte codes. And so rather than directly interpret the things, we want to continue assembling. So just at the next address in memory, put this. Okay. And so what you see here, this is a macro. I talked about what this did earlier, but it says what's in the caret register. Put that number down as 4 bytes, which is these 4 bytes right here. And this is wrong. This is absolutely wrong. And I'm going to fix this in a minute. So these 4, says there's NT return and equal NT return. That's the thing we just defined in here. And then the very next thing we're doing is put this here, and this should be 0, right? So by default, we've just started the machine. We've cleared the memory. We've cleared you reset everything. This should be 0, and instead it put this symbol down. This is wrong. So I have a bug in my assembler that is putting this number down rather than the number it should be, and so there is no linked list. And this is why my you haven't seen. I haven't even gotten to the bug yet. But the bug is that if you get to the end of this code, we're trying to find a word in the dictionary, and well, it can't, because the linked list is not being generated correctly. If I go to the Pascal version of this, can I do that? I can't, because I don't know how to scroll in Pascal. I don't remember how to do this. I don't even know if you can do this to scroll up and down in memory. I think you can, but I don't know how to do it. So I'm not going to go down that rabbit hole right now. Where was I? Up here. So this should be the number 0, saying that this was 0 when I invoked it. All right, and then what it's doing, okay, so opcode 4, well, if we go back to the binary number 4, it winds up being 0, 1, 2, 3, 4, so that it winds up being control D. And so it's showing up as control D, but it's not actually this is data, this is not code. That's part of the problem of working in assembly, is that, or like looking at these memory dumps, is that, like, what do you show? Because I could show the number 4 because it's a hex byte that is the number 4, but in my instruction set, that byte is this instruction, right? Is control D, which means invoke whatever's in the D register. I don't want, but what it really is a 4, right? It's a 4 saying, because if we go back here, right? If we go back to the structure of the dictionary, sorry, stop it. If we go back to the structure of the dictionary, we have 4 bytes that is the pointer, which again is wrong here in this thing. This should be 0 because there is no previous entry. The pointer to the previous entry, and then we have a counted string. So we have a string that the very first byte is how many bytes is it? So there are 4 bytes. So this is the string E-NM for entry name, E-NM. And for whatever reason, it's smart enough to know that, I guess the rule is that it shows it in ASCII, right? It shows that if it can. It's showing it as an ASCII number, as opposed to, like, this is also a instruction code. Okay. But anyway. Okay, so now this is just some data that's been stuck into memory, and the assembler, like, there's no, all the assembler does is stick bytes in memory one after another. And so if we want to construct a dictionary, that is not the assembler. That's something we're doing in the assembler. And so here I am. I do have this macro here that says that's supposed to say put the address of the last time I used this macro, which should be 0 here. And then literally when it sees this number 04, it should put the number 04 here, which it did, which is why that just happens to be the same as control D. And then back the assembler syntax for quote or apostrophe E is put the ASCII character E into, so whatever byte this corresponds to, that is being stuck into this memory address. And so the assembler is just laying down one byte after another, and that's what we get. And then we reach the end of the line, we're done, we're back in interact mode, and then we immediately tell it to go back into instruction mode, and so assembler mode. And now we're going to give it the label ename is 11C, and so 11C is, if you look at this column, it's this byte right here. So again, this is disposable. This is something inside of Decker's. This is data structure in Decker. It's not part of the virtual machine. And so these two lines are doing the same thing, but for different levels, right? So this ename, this string right here is creating a label inside the assembler, so that the next time we see the word ename, like down here, it's actually going to emit a call to this. It's going to emit the instruction CL, which is call, followed by the 4 bytes that are this address, whatever this number right here. So it'll say 1C control A and then 00. It could, because it's a little endian. All right, so at some point I'm going to be able to juxtapose these two things, and you'll be able to see this, and then right underneath you'll see the code that assembled to it, or that it assembled to. And I want the debugger to work that way too. So I don't have to. I feel like I'm explaining the same thing over and over again, but it's so confusing. But eventually this will be on the screen, and either they'll be mixed into with each other, or you'll be able to click on this and it'll take you right to that point and show you exactly what this compiled to. So this doesn't actually emit anything; it just makes a label. Anyway, then we say load byte 4 AD return, load byte 4 add return. So add 4, and again, if you think about it, you're looking at this point in memory, and in your entry in your dictionary, and then you want to get the name. Well, you have to move 4 bytes because this is 4 bytes. So the pointer is 4 bytes, so you have to move ahead 4. And so to get the name, you load the byte 4 and add it to the address, right? And that's it. So that's what ename is. Okay. And so, but by doing that, now this right here, like, is the first dictionary entry, right? We don't know how long this is. So this is the entries can be as long as you want. So size varies. Size varies. Size varies for the name, but it has a length byte. Here, there's no length byte. So this just you don't really know when it ends. All you know is that where the next entry is. So this probably ended before, somewhere before this started. But you could have labels for parts of a function or something like that. You could have a label inside of a function because you want to do like a goto or something. Anyway, but the point is that for the purposes of exposing this function to the world, we want an API so that you, as a person talking to the virtual machine, like you've got this embedded in your your JavaScript program or your Decker program or whatever, and you want to call something inside the virtual machine. You want to be able to get access to this dictionary, and so there's the BIOS is going to provide that for you. So rather than you having to say, okay, I just implemented it in JavaScript. I've got a copy of this virtual machine. I've loaded the code I want to run, and now I want to run a word, and so I have to parse this dictionary myself. Now in JavaScript, I have to go look in this memory and figure out how everything is structured. No, you provide the BIOS, and so the BIOS is, I'm going to give you a string, and I want you to now, I'm going to put that string in memory somewhere, and there will be a dedicated spot for it. In fact, that's what this is for, right here. So again, this is wrong, but there'll be a dedicated spot in memory for you to put, for you as an outsider, you as the controlling language, the host language, to put some bytes, a string into memory, and there'll be a function. This is like add token or something like that. This will be part of the standard API of the virtual machine from Python or JavaScript or whatever. There'll be a function called like send token or something like that. And what it will do is it will put the string, the JavaScript string. So you type the word, in JavaScript you put like words or whatever, or e-name or whatever, and you call this function, and what that function is going to do, it's part of the API of the virtual machine, is it's going to put the host language string, going to convert it to bytes in the memory of the virtual machine, and then it's going to, and then what you could do is then you could say execute. You could invoke this thing, and the idea is that with you put the address of the string there. So the address of the string is now on the stack, and so on. So for example, here we have again the same thing, and I put it in a register T. So if I say add T, and then I say Control F, F is find. I have the find verb is up here somewhere. So F is associated with this word find, and what it's supposed to do is it's supposed to read. It's going to grab the tail end of this thing. And this is horrible to look at because I put it all on one line. But let's find F in here where it's all nicely formatted. Oh, come on. Oh, I didn't give it a name here. But it's this, and the idea is that we're going to, grab that last. We're going to look. So this is says look inside this register, and this is the register to look in. And then these are more macros that say while it's not 0, do this. And I'm not going to talk about what these do, but they work like while, and it's like a while loop in Python, right? It's what it actually does is compiles jumps and stuff, a bunch of instructions that make it all look nice, but you don't have to worry about that. That's a whole other topic. So basically, we're going to loop through the dictionary list starting at the end, and duplicate. Most operations in these languages are destructive. So like again, if we say, you know, 2, 2, that puts two things on the stack, and then when we say add, we're destroying those two things and putting the result. Oh, but I put it again, right? Because I didn't delete the 2, 2. So you see they're being destroyed up here, and the 8 is going to go away if I hit zap, right? Okay, so the point of that is that things are destructive, and so if you don't want it to be destroyed, like if you want to hang on to your 2, and you say add, what you really want to do is say, you know, you want to put a 2 again. But if you don't know what it is, rather than saying 2, 2, you can just say do. And then what it does is it duplicates it. So 2 puts the 2 on the stack, and then do duplicates it, so we get 2 2s, 2 2s. And if we put a, you know, whatever this hex number is, and we do that, we duplicate that, if we zap it, whatever. And then there's another one called like swap, which swaps these 2, and then we can, see now we've done some operations. We may not know that there's a 2 up there, and we say do again, we get that. Anyway, these are just, they're called stack operations. These are some of the standard byte code, or bytes in the instruction set. Okay. Anyway, so but you see you use this word do a lot to duplicate things quite a bit. So it almost looks like a this dot or a self dot, like a this dot in Python in JavaScript, or a self dot in you know, or X dot in thing. So ename is like whatever we have on the stack, get the name address of that, the address of the string, and then T is the token buffer. That's the address of the string that we've put into the system. And so now what we're going to do is we're going to look at these 2 strings and see if they're the same. And that's not a built-in. That's a function that we have to write. But I store the address of that function in Q for query, or for equal, actually, I think. But yeah, it's you can change these at runtime, so it's an arbitrary query, but by default it's the query is are they equal, right? And so again, there's some assembly code that does. I'm not going to go through what this assembly code does, but you can kind of see it in the Python translation on the side. So are these 2 strings equal? Well, you know, if are S and T equal? So if they're the same pointer, then yeah, they're equal. If the length byte is equal, then they might be equal. But if the length byte is not equal, then obviously we can just skip out and return 0. And then you know, now we're going to say if the lengths were equal, then we have to compare character by character, and so that's what this all does. And you can see, you know, this plus S or whatever is something that is like reading one character and moving ahead. And that's all I'm going to say about what this does. So I've written this all in this B4 assembly language, and you know, it kind of works over here. Let me do this quit. And so in the Pascal version, what this does, I type words, it's putting that into the buffer, right? There's a specific spot in memory. It's putting these letters into that buffer. It's remembering the count, and as soon as I hit space, it's going to look at that buffer, and it's going to do exactly what I just described. So it's going to call this function, this function, and it's going to loop through the word list, which it's already printed out once, and it's going to find the word. It's going to print each one. But in order to do that, it has to know what does words mean, right? So words is the word that prints this out. But when I typed it in, it has to loop through the list to find the word. So it's going to say free. Is that the word words? No. alloc. Is that the word? No. Okay. Comma. No. Here. No. Put in words. Oh yeah, they're the same. So in theory, it should say, okay, that's the same, and then it should say, okay, now that I know that this is the right entry, now I'm going to return the address that I was looking at. So I made a copy of it. We established that they were the same, and if so, now I'm going to return the address that I found. So I found that to be correct. So return that. And of course, if it gets all the way, you know, if I made a typo or something, if I say words, words E or something like that, it's going to get all the way to the end, and it's not going to know the word. It says unknown word. Unfortunately, yeah. Unfortunately, the first time I run it, it works. So it found it, it executed it. Second time it fails, and I think that's because it can't even find it. Third time it's going to say it's going to crash. So that's a bug, but I'm pretty sure that's a bug in the character handler here. it's not a bug in what I'm showing here. So I haven't gotten back down to that point and fixed it yet. So it needs some cleanup. But because it worked the first time, I'm pretty confident that this works. It's just something else is screwing up externally. Now I took that same code. I've taken this code and I basically just copied it here, and I streamlined or cut out all the comments and everything, and just tried to I'm just trying to debug something. So I wasn't expecting to show this to people, but that's why I keep going back to this. So this is the exact same code as this, and now in the assembler I've just added another string. Now this is the string I want to find. And my goal was to say, okay, well, are they, I can say now, so the goal string is this. I want to find ename. No, sorry. This is the name I'm looking for, right? Wait, what? Oh, I see. I'm making a copy of that string so I can look for it. So somewhere up here, we've already used the word ename, and it's in memory. Right, so just by doing this, now I have an entry in my dictionary, right? Like if the dictionary is a linked list, then by default, before I ran this line, right? Like if I clear everything out, right? And I say I say that now, oh yeah, I put the number 0 up here, right? If I look in here, it's 0. And so that would tell me I'm at the end of the list, and so my dictionary is empty. And then if I just run this part, well, it's not going to work, but okay. If I just ran this part, and now I look at that, I do the same thing again, and I say look at the last entry. Okay, so that part worked. That is correct. But what it should have done is it should have laid down a 0 here, and it did not. What it did is instead it laid down the character, right, which is wrong. All right, so I'm gonna fix it. I'm gonna show you how to fix it, and then we'll show you how it should work. All right, so now I'm in Emacs on my local machine, and I'm going to look for the word macro. This is the Lil code. This language is called Lil. It's the scripting language of Decker. And I'm going to look for the Lil code for the list builder. And what I suppose this is, I have a very terse coding style, so this is probably just as cryptic. But so we're saying, is C equal to this? Yes or no? This is like a double equal in JavaScript or whatever. If it's so then like, imagine the word then is here, or curly braces or whatever. Lil does not need those. So, and there's no semicolons or anything like that. So we're going to say A is the here address. So here is the word here represents the address of the last byte that we put into memory. Up here we have the word emit I, or emit integer, which is like a little, oh, yes, well, of course. Yes, that's what's happening. It should, what we want is to get the register. We want to get the value of that register, and instead it's just emitting that character. And so that's why we see this here. And so this should not be here. What this should actually be is all zeros. And if I put this down here, so I save it, and now you'll see how to, you can write code as much as you want inside of Decker, but there's this thing called modules, and just like a way to, it's just a way to keep this in its own little text file, basically. But now to load it interactively, Decker is extremely sandboxed. So there's no, by default, there's no just like load a module from disk. So what I do is I take the file that I just saved, and I drag it here, and then this pops up a dialog, and I say, get rid of this module, and then copy this one over it, and it puts it in here. So this is all like, these are all like little widgets like this this thing I made up here that like has all my scripts in it. That's the item list. And then these are other things that I made that like, this is the B4 console. So you can do all kinds of stuff with Decker. It's not about Decker today. Anyway, so now I've copied it over, and if I do it again, it'll make a module. It won't make it just calls it module 1. Anyways, this module exists now, and I say okay. And now because I fixed that, I'm hoping that if I run this again, so this is right up to the word. I don't want to lose this. So what I'm doing is deleting it. I'm copying it to the clipboard, running it, and then pasting it back. So if I run it again, and I'll go ahead and put the this line of input in here, so I don't have to type it manually. So I would expect this to stay the same, but then when we look at the memory here, it's going to change. It's not going to have that @ sign there anymore. All right, so we run this. I don't know why that changed. Maybe I didn't have, maybe I didn't have these lines in here. But oh right, because I wanted to see. Right, sorry, let me do this again. I wanted to just get the. I wanted to do it here. So we'll do it this. Nope. Right, sorry. Question mark caret. There we go. All right, so now that's what it was before. And if we just look at the memory here, these are all registers again. And then when we get to 100, it's empty. So that's what it was. It was explicitly assembling that character rather than the contents of the register, which is stupid. Okay, so now I expect this to actually work all the way through. So the bug should be there. And so now, oh, but that did not work. Because now if I do this, 19E should be the address of the last thing. Yeah, this is right. This is I checked this earlier. This is the address of the last. Not the last thing here, but the address of one of the labels, right? Sorry, the address of one of the dictionary entries. 19E is right here, and previously this had said it had shown that little caret symbol because I was compiling that caret symbol as opposed to an address. So this is this symbol right here, this symbol right here, and these two these things, these 4 bytes create a number that is the address of the next entry. So if I say that looked in the caret in the register that is holding the end of the dictionary, and it put that number there, is the one we inspected and saw here. So we put that number there, and now if I say read integer, right? This is we've got on the stack we've got a pointer pointing at this, right? And in binary, this is going to be let me show you what this is in binary. Because I want to make a prediction here. I want to say that if we how we do this, okay, parse. I want to use that to parse, and it's this and this. Oh, shoot. All right, so 9.1, but then we want to format this as hex. So we say I'm in the lil listener right now. So 5B. So what I expect to see when I do this is I expect to see 15B show up on the stack. And there it is. Why? Because I saw this number. So I know that control A is a 1. I know this number is written in little endian. So I expect 0, 0, 1, and then whatever the hexadecimal code for this thing is, which I discovered was 5B. By doing this is like saying, hex ord of the character. And it told me it was 5E, so then I expect this to be the number 15B in hex, and it is. All right. So what have I done? I've started at this address, which is the end of the linked list. I've read from memory the value that is at that address. Right. So I followed the first link, and if I read it again, right, that's that. I'm just this doesn't clear, so I'm just going to keep typing that until I get a 0. There we go. So that's my dictionary. Those are the links of the dictionary, and all I have to do to traverse the dictionary is this one instruction. Is that, you know, given a number on the stack, this puts the original number on the stack, and then I just call this a bunch of times. And so to iterate, you know, in a loop, to go through that whole dictionary. Oh, sorry, I'm looking for this one. That's what this find is. So it's just calling RI. RI is not actually one instruction. But it just sets a flag that says values are 4 bytes long. Read a value, return. That's all it's doing. It was an instruction at one point. Probably will be again. So that's it. That's why this while loop traverses the list. And for every item, we have an address. We duplicate that address. So that we get another copy of it. We can make a temporary copy of it. Check the name. Check it against the token buffer, and then run this Q function, and then the Q function returns either yes or no. Well, it's supposed to return yes or no, but it doesn't. It seems like it does not return yes or no. Because what we should see is if like if you have two numbers 5, 5Q, it should say, okay, well these are the same pointer, so they should be the same. We should put a 1 up there. It did. Okay. All right, so this part of the code works. If S is T, return 1. That works. Now something's going wrong. That if we say, well, okay, somewhere along the line, I also made this. So this line right here, Control E is now going to emit a character. So it loads the byte E onto the stack and says IO. So if you say like H, which pushes an H, the ASCII code for H on there. Oh, I could have just done that, didn't I? If I wanted to know what that was, I could have just put that. I said 5B. And so now if I say if I say that and I say IO, it's going to emit that character to the console and it should print this out, right? And pop it off the stack. And if I do it again, it should print that H. Okay. And if I print this, I don't know what'll happen. Yeah. Lil and Decker only know how to print ASCII character, visible ASCII character. They don't know how to print this binary thing, so that's printing a question mark. Okay. But okay, so that's emit a character, and then W, Control W is write, and so this little I'm not going to explain exactly what it does, but you can see .f is for 4 and n is for next. It's a for next loop, so it's looping through the numbers, and then it's using r as a variable. And I guess I am explaining it. It's going to emit, it's going to read a value, move 1 forward, and so on. And you have an address of a string in memory. You're going to write that address into register R. You're going to read the value that is. You're going to say read bytes. Values are bytes. Read and then increment by 1 byte. So you read the first byte, which is the length of the string. Now the length of the string is on the stack. Oh, sorry. This just did the increment, and then RV reads that value. So now you have the length of the string on the stack. And then this for loop thing, again, this is not a bytecode. This is a macro, so it emits a bunch of, it emits a couple of instructions. And it remembers this address, and then N is going to figure out how to jump back to it. But it like pushes this to the control stack, and it doesn't matter. It's doing a for loop. So if the length of the string is 4, it's going to do 4 loops through this. And what it does is increment the read pointer. We just arbitrarily use this as a read pointer. Read another byte, and then emit it. So this is printing a string. And so I can say at T, write what I have in T, and I have that string right there. And then I think goal, somewhere along, I gave an extra name to that dictionary entry. Oh, actually, I decided I wanted to actually look for XT because it was confusing for some reason. And now it's super confusing. So I actually want to look for. So I'm going to rerun this, and then I'm going to say at t write, and then it should say ext. So this is the execution token for the entry. Execution token just means the start of the. It's the address of the start of the code. So after the label. So basically, if I'm looking at ext, so here's the dictionary entry. This is the address I have on the stack, and I want to jump over this string, jump over the address, jump over the string, and actually get the address of this, which is a call to this function. So I want to traverse the list and run this queue on every one and see when they match. So queue seems to be broken. This query seems to be broken. This is just like I'm pushing stuff onto the control stack so that I can restore and save and restore the values, the original values of these things, and reuse them. I don't screw things up. But the point is that T and then Control F for find is, I've used the same label here for find. F and find are the same thing. Oh, it did. It found it now. Oh, right. Okay, right. It found it because I fixed the bug. The bug was that I was, instead of doing the linked list, I was right. Instead of doing the linked list, I was compiling instead of writing down the address of the previous entry, like here, it actually just had that. It was just compile or assembling the character for the pointer, the caret. Okay, well, anyway, this is fixed now. So I guess I don't know if I've explained it well enough or not, but the idea is that by doing this bit right here, I've assembled. The assembler allows me is one way I have of putting stuff into the memory of the virtual machine. The other way I can do is I can just say, well, okay, you can say. I'll screw things up a little bit. I'll say I can use the source language, right? The lil, I can use lil here. So if I MB4 is the module that I have, and if I say get VM, now I actually have the virtual machine as a lil object that I can mess around with, and then I can say mem, or I can even just do this and say vm.mem. And then if I want to put some stuff here, I would say like 04, and I'm going to say ABC. I think I can do this. I think this should work. I could be wrong about that. The syntax for this is a little weird. It's let's see. And then, yeah, it did it. Okay, so now I just wrote directly to memory there. And the idea is that you can do this from JavaScript or whatever. So if you know the place where you want to write memory, then you can just treat the virtual machine's memory as an array of bytes or characters or whatever, and you just stick the string you want to stick in there into the right place, and then you can invoke the BIOS. So ideally the BIOS would have two parts. One is the part that I'm writing here in the machine, which is this is done, or this part of it is done. And then the other part would be an API that you call from your host language, so that instead of doing what I just did here, I would call something like VM, put token, or via set token or something like that. And set token would be the thing that puts it in the right place. Because here, like I just put it at address 0, but it really needs to go at wherever the token buffer is. You as the caller of the language shouldn't have to know that. It's just, maybe even call it like input token or something like that, or set input or something like that. and then tell it to go, and then it would actually run and do whatever you wanted it to do. This is just makeup. I've just made this up right now. It's all imaginary, but that's the intent. So this would be like the other part of the BIOS that actually lives in your and BIOS is not the right word for it, but it's what I call it. Like the input-output system is that it lives in the host language and invokes the machinery on the virtual machine. You don't have to run this, but so the virtual machine is just blank. But if you run, the idea is that multi-core, right? And so like by default, what you would do is you would fire up the virtual machine in your programming language, and like just some of the cores would be like the first core would be reserved for this BIOS stuff, the dictionary handling stuff, and maybe there'll be another core that does like that is set up to do the input and output from like standard in, so you get like a read line for free. Well, not for free, because you still have to talk to the host language. Still has to do some interaction with the operating system or host language or whatever to set up the virtual terminal. But like once you do that, once you do like the bare minimum to get that set up, then you ought to be able to hand control over to the virtual machine and get like a read line like library for free that would be living in this virtual machine. And likewise, writing color text to the screen, like all that can be handled by the virtual machine. And it'll be very small. Like it'll be written in this bytecode or whatever. That's the idea. And so you would get a nice high level interface to this to the machine, and so that allows you have a standard place to put the string from your host language. You put it in there, you read the string, you go byte by byte, and you get the you look it up in the internal dictionary. And this, because you're just firing off like from the host language's point of view, there's a register called X, and you're just going to fire off Control X, right? That's execute, or I guess Control F would be fine. Find that word, execute it, right? So you can put the word in, and maybe that's what this Go thing does, right? But or maybe it's like this, I didn't say that. Maybe it'd be like VM put, or set input, and then you would say like whatever you want to run, my program or my script or whatever, and then dot find, and then dot execute, or and what find would do would be like run find would be like run op F or whatever, Control F or something like that. I don't know. I haven't gotten that far yet. But yeah, so in the process of writing the virtual machine, in order to get it under test, you have to provide like the bare minimum like interactive mode for this. I call this program B4I, B4 interactive, and it has like all these labels and things, and to do the test harness would be a simpler program called B4H, which is like a subset of this line, and you have to write that. So you don't necessarily get all the stuff like the labels and whatnot, and the macros and whatnot, but it just bare minimum, in order to implement the virtual machine, you have to provide like a subset of this, and so you already have a function that can do basic assembly stuff and do basic invocation of one opcode at a time. And the hope is that given that bare minimum, we can build this, and then you wouldn't even have to have like so this B4I is a higher level language written in Lil. The idea is that you would only have to implement the handler, B4H, the simpler language, and then you could use that to load the more interactive thing onto into your language or whatever. So there's a bootstrapping process, right? Like I want most of the tools for this to be written in this assembly language, so that if you're working through this course, you spend a day or two, afternoon maybe, writing this virtual machine in the language of your choice. Or if you're not that far along, you just, as a programmer, you just download one. And now you can start building things from scratch using the virtual machine, with this nice interactive system or whatever. Obviously, I have to put a lot of thought into how I'm going to explain things and how to present that to make that doable. But this was the first step. So now, now what I've accomplished here today, which was really like 5 minutes of work in this 2 hour, however long it's been, talk, was all I did was 2.5 hours. All I did was I fixed a bug in the assembler that was this right here was actually just, instead of putting down the previous address, it was putting down that caret symbol. And so that was screwing this up. But now, because I fixed that bug, I've got this same chunk of BIOS code that is running in the Pascal version and in the Lil version. It doesn't actually execute it yet, but that could be the next thing. And so I guess really well, I mean, I should do that, right? All right, let me implement this. Well, okay, so in low code. Oh, that's messy. What is happening here? Oh, this is it's because I know why. Because this thing is on top. Hit it, move to back. Ah, you thought it was a scroll bar. It's not a scroll bar. It's just called a slider. This one actually is a scroll bar. And that little button is also, wherever this is, also on top. Say file, edit, move to back. Okay, so now in Lil, let's say this should be Lil code. So if we say alert, hello, and if things are still working and I hit shift enter, that should run. Okay, so hello, it does. So that's Lil code. So we can take this and we can say this, paste this here, and then before step. And if we do that, then it would actually update the debugger. This is unfortunate, but we can move this here. Wait, no. Edit. Back. There we go. This is the one I want. Edit. Move to front. This one over. So the point of that was that that's dumb. I mean, that's what it's supposed to do. I'm faking tabs, right? There's no tab control here. But so whatever this button does, let's see. We just have to know the name of this thing. The Lil scripts. I just won't press that button again. And then here, Lil scripts dot show equals solid. It's really fun playing with Decker. Oh. There we go. Okay, so now we can run this and it'll actually update the thing. If I run this, I said ABCD, now we can say banana, right? And it's only going to take the first 4 letters. Maybe I have to actually say show RAM. Oh, because I didn't say what VM was. Okay, so VM is MB4. No, I did. VM is MB4 get VM. Maybe it didn't like that. So how about we say 1, 2, 3, 4. What's going wrong? I put the 1, 2, 3, 4 there, but it didn't do it when I wanted it to. Before step is the one that this and then draws the stuff. So it used to be called show RAM. Before step should do this. I gotta change this. So it's not doing it. I think we say card send before it's a card event before step. It is possible that there's a bug in this code and it's not showing up. That worked. Why didn't it work here? Oh, I know why. I know exactly why. This needs to be deck modules MB4. So say MB4. You're not supposed to, yeah, because the way this is not built into Lil. I made this, so I have to like emulate what Lil does at every frame value. So it now get the module, and then we say VM is MB4 get VM. One thing I struggle with in Lil is that you don't have you don't really have error messages. Although I am probably suppressing an error message here. But a lot of times, like if you just say like you make up something and you run it, fine. It doesn't care that that function doesn't exist. It doesn't matter. it just by default returns 0, and that's good sometimes because now you can send a message to say like, you know, update something that may or may not be on your card, but whatever. All right. But it makes because now things are working. Okay, so, and I bet we don't even need this. I think we can just say before step. But we'll see. So we got to change this to like another thing. The test is whether the X shows up there. Does not. Okay, so we do need this. There we go. Okay. All right, so now that we can get some input and output, what was I going to say? I was going to say, okay, so let's make a thing that says we're going to make Control H be is going to be. Let's set this string to a string, and we're going to say there's 5 letters in the string, and they are H, E, L, L, O. And then we're going to say, when H runs, we're going to say, get the value of that string and write it. And then, so if we run this, boom, and then we say Control H, it should say hello. Ooh, it does not. 1, 2, 3, 4, 5. What's wrong? Did I already use S maybe? I do not know why that is there. That is not what I expect to see. Hey, John is the person that made Decker. In the little script on the list contraption that evals code, you should assemble a dictionary that gives that snippet of variable bindings like the local variable in the listener. Yes, I agree. That makes perfect sense. In the code that does this. So how that actually works is I have in the deck itself, you can put a script. And how do you find that? You say file properties and you say script. And these are like, yeah, so this should really be, I think one of these arguments is a dictionary, right? That needs to be that, so D would be like D.mb4 is modules, deck modules or whatever. MB4 value, something like that. And then like that, but I don't know which one is which. So see, help little reference, and then find eval. Or maybe eval is in the Decker reference. Yeah, this eval. using any variable findings in dictionary Y. So yeah, and I don't know what Z is here. Z. Third argument is truthy will execute within the caller scope, which I wanted. So yeah, so this, I had it right. I guessed right. And I guess, well, how would I know all the, I'm gonna have to go in a minute, so, but how would I know the, like, how would I know that B4 there, whatever, this is a good first step. So hopefully I don't need this anymore. Let's try this. We'll just run this, and this works. So again, we change this to whatever, and we expect this to update. Yeah. Okay, so I no longer need that line because of that change I made, which is again a cool property of Decker. All right, so I don't know why this printed out. That doesn't seem right to me. That should have printed out a number. It should have printed out a X number. You know what I bet that was? I bet I had that string on the, I bet if I, no, because it wasn't input, because it would have said like that. I don't know what happened there. All right, let me try this again. All right, yeah, so what I should have done is put the number on the stack, which it did, okay. And that's the address of it. And when I say write, that should write that string hello. Oh, because I put an O instead of a quote O. All right, so now, if I do Control H, which is defined here to be @s write, invoke W, and it still panics. @s I think what's happening is what is happening? I don't know. I have there's probably a bug in the way that the immediate execution of these are happening. I don't really know. Or even, yeah, I've definitely got some bug here. I don't know. I'm not going to try and debug this because I got to go in like 5 minutes. But I will make this. So what I wanted to do was, all right, so we have the VM. And yeah, this interface is not nice. But what I want to do is I want to say VM ops how do I do that? Yeah, so the interface for just like calling this from a programming language is not worked out very well. I think I want to say VM op im for immediate op. I don't know. I might not be able to do this like this quickly because I haven't thought this through yet. Im immediately invoke a dictionary register. R. And I also don't have an operation to do. So what I want, if I want to invoke right, so I think what I do is I say 4 times, because they're 4 bytes each, and I want to say, yeah, I'm not going to be able to do this today. I need to think through this and like design some stuff here. This is not something I should be doing on the fly. But I want to parse the ASCII code for the register that I want. And in fact, I bet there's a, this is in the, it's called reg A, I think. No, it's called reg. But this is not exposed. So mod reg is this. So, and then we'll do the installation thing again. I just get used to doing this. I'll say remove, copy, boom, and then so we don't need to do this anymore. So immediately invoke reg. And which one do I want to invoke? I don't want to invoke it. What I want to do is get the register of the buffer, the token buffer. Which is this, which looks like it is meant to be private, because it has an underscore there, but now I need to rethink that, because I wasn't thinking about the public interface for this. All right, so let me try this one more time. I'm going to wrap this up here in a minute, because no fun watching me stumble through my code here. Or I hope maybe it's fun, I don't know. Right, what I want to do is, if this works, let's try this. So MB4 get register, get the contents of register. That should give me 256. It does not. MB4 gr, does it recognize that? It does see that. Oh, it's all blank though. Do this, and then get the register, the value of the pointer. See if that works. Yeah, 414. And if I hexify that, (19E), and then if I say, yeah, okay, so I'm successfully reading a register here. So MB4GR is reading a register. So MB4GR of T to give me, so T is going to be the address of that. Then I would say VM, called RAM or MEM. I need to standardize this. I think it should be called MEM. I think it's called RAM here. Yeah, it's MEM. Okay, MEM is right. Pascal version is called RAM. I'm slowly replacing it to. So if VM, you could have just looked at the console here. And so then I want to say T, and then like the next 4 items, or I guess if I want let's see, E name, that's 4 characters, so I want 5, and it's going to be, I don't know if I can do this. Probably not, right? Let's see. The reason I wouldn't be able to do it, see, so where is T, right? T is what? That's the value of T. What is T? T is 8 is 80, but what is it in hex? This is terrible, right? Yeah, so I want to do that, and I want to look at this address, 50 BDA. Okay. So 1BD is now the address of the actual hex buffer. 1B. Oh, and there's the word hello. No, but that's not right. T is EXT. All right, so previously this had said if I assemble this, we look at 1b4, so it says D, this is the 4, E, xt, and so here I've replaced that with zeros. I did not replace it with the string, and the reason is it needs to be so we want to take the ASCII character of each, or the ASCII value of each one, and now it'll be ename. So ename, and in fact we could make this 2 b4s, or we'll just call it b4s for b4 string. On b4s s, we would say this and then prefix it with the count of s. Oh, array cat, okay. This alarm is telling me I have to go get my daughter from a bus stop. So I can either end this stream now, or we can take a 5-minute, 10-minute break, because I don't know when the bus is going to be. Maybe what I do, I've kind of like I fixed the bug in here, and I've rambled a lot about this. So maybe I don't want to just have dead air for all this time. So I think what I'm doing is going to wrap it up, take a little break, and maybe come back in an hour or two. And I don't need the comma, he says. Okay, count s. And I don't need this. Or you don't need that in your. Let's see if this works. And then b4s, and we're going to do like ABCD. And if I do this, did not work. I say do. There we go. So that did something. I think this did need to. I think that was not meant for this. But there, that worked. All right, so there I put something in memory, and then the idea would be the next thing I would do is actually invoke this BIOS. BIOS meaning look it up and run a piece of code. I gotta go, so I'll be back probably an hour or two. I'm gonna cool down. It's really super hot in here. I'm gonna get something to eat, and I'll come back later today, and if I can. Oh, I guess my wife is going to the bus stop. Thanks. Well, in that case, I do want to wrap this up pretty soon. But let's just go ahead and do this. So the thought was get register t, or get the value of register t. That's t. Okay, so this is kind of part of the. So get the VM. I'm gonna need that first. Maybe these should be all added onto the VM object or whatever. Lil does not really have objects. It has dictionaries and whatever. In fact, a module is more like a traditional object than dictionaries because it has state. It closes over something. Okay, so anyway, so I want to write that into memory. And then I want to find it. And so that would be executing an op. And so that would be well, I could run b4i. I could write mb4 b4i and just execute whatever I want to execute it immediately. And so that would be at t find. And then I can look at the TOS. So I'll alert the TOS, the top of stack. And so in theory, whatever I do when I type TF, it found the address I'm looking for. And then the next thing I want to do is execute it. That panics because it doesn't have a name to look at on the stack, I think. It didn't have anything to look at on the stack. So let's instead so I guess what we actually have to do is we want to put a new entry in the dictionary that's called hello. Sorry, we'll call demo. And then here, okay, so run this. Last entry should be called demo. So if we say at this and write it, no, at this or add and write it, so the ename, oh, it's called exec. Why didn't it work? Because I put this instead of this. Run this, it should say demo, but it didn't work because I didn't put a length on this thing. So put 04, run it again, run this, and it says demo. Okay, so now we'll put the word demo here. Boom, and it did not find it. Okay, so if that ran correctly, and we say right here, it should put we should see demo again. Word demo is here. Oh, no, right. No, okay. So by default, this is the default value of t because I've set t as this going to be here. I put 4 bytes down, and then this should have written to it. It did write to it, and t should not have changed. Maybe I didn't run this yet. Okay, t. If I write this, it still says ename. Oh, because I wrote it to t. I don't want to write it to t. I want to write it to. Maybe this was private for a reason. Yeah, that should be reading the value in RAM at that register. I say string t is 1BD, and if I say hex format MB4 get VM RAM MB4, or no, I just want MB4 get reg t, right? One BD. I did read the memory correctly, okay? So if I wait, hang on. It's a string. I said format. I don't need I didn't format it. So that's actually the number. 445. So T should be 445. Get the virtual machine. Get the next 4 bytes, the 5 bytes of the word demo and the count. Set it. I don't know what's going on. I can't understand a single thing. Oh, sorry, you jumped in the middle of this thing. Sorry. Yeah, this is not an expository thing. This is a debugging session. There was a lot of exposition preceding this, but now it's now we're in the weeds here. I'm very confused. So I think I know what's happening here. I thought maybe I know what's happening here. I I mean, this is the address of that, right? Okay, so I run this. Oh, it did. I say it's writing it here. This is not the right address. What am I doing wrong? We said that this 1BD is the address is where T is pointing at. 1B. So 1B is this line right here, and this is the old string. I did not put the word demo here. I did not succeed in putting that there. One, two, three, four, five. It is writing here. 1BD. It is writing at that spot, but not when I did this. Right, so this is wrong somehow. B4S demo in brackets. I'm expecting a 5-byte string, and I got that. Five bytes. Oh. Wow, that's dumb. Yeah, I copied and pasted it. Thanks, John. Okay, so it was always writing the hard-coded string. All right, so now we can do the right thing. Demo, B4S demo. Okay, so now we have the word demo here. And if we say @t and then write it, we get demo. Okay, that's what I want. All right, so now can we find it? And I think the answer is yes. I think what's happening here is well, hang on. Okay, let's see what's running here. So we run it and it's spinning forever. Okay, that's not good. We say script stop. So why is it spinning forever? Didn't get this far, didn't get an alert. D is the number, control D is the number 4, so this is 4DEMO. That's correct. Everything's correct there. So it did this. Everything up here is so far is correct. And then this is not. This seems to be failing. But let's say, okay, so now somewhere in here. Oh, so previously in here, I've encoded a goal. So somewhere up above. No, this is actually wrong. Because the goal now contains the. Yeah. Okay. So some. Oh, right. I see what I'm saying. Sorry. I'm at a point now where I have no idea what I'm talking about because I'm debugging something. But I would expect if I just run this and let's call this S. No. I did it again. Okay. All right, let me try this one more time. Just by doing this, I should have an entry in the dictionary, and it's the last entry in the dictionary. And before I do this, I want to say, so I've put this string in here. Now I've assigned a variable that also has a copy of the string. And if I run this now, what I want to do is I want to find that string in the dictionary, and it should be the last one. So that's the end of the dictionary, 1C2, and that should be the address of this string, which it is. 1C. No, sorry, it's the address of it's the address of this link, and then 4 bytes later is the address of the string. Okay. And so if I say at sFind, what it's supposed to do is find it's supposed to find that string. Sorry, sFind 1CB. It found the string, but oh right. Okay, so it found it did, that's it. No, hang on. It's returning the wrong item. This is embarrassing now. I had a nice little stream going, and now I'm just confusing myself here. Yeah. Okay. So find. There's something wrong with find. It's not doing the right thing. Or I'm passing the arguments in the wrong order. What is find? Find takes an address. At every point, we should be looking at the the item on the left, right? What I'm calling S. S is the thing defined. Oh, have I defined F? Where did I define F? I did. I put it right here. But okay, I see what's going on. This is not right. No, it is. It is. I thought I was interfering with the dictionary, but no, this is right. Everything here is right. I just copied and pasted this, right? So unless I screwed this up, which, just in case, let's put it back again. I need it all on one line because in this buffer, I'm actually using the real assembler, where at the start of every line, you're in assembly mode. But in Lil here, I don't have I just, it's a couple lines to make this, but I haven't made this function. So at every line, at the start of every line, you're in interactive mode. And like I said, I'm going to wrap this up here because I don't want to just like flounder on screen all day. It's no fun for anybody. But I will finish this and then so this is what find should be. And I'm actually in the terminal here, so I have to copy it this way. I think that's probably exactly. Come on. Oh, okay. So there's a slight difference. What's different? A space here. And it's exactly the same. Oh. Okay, I don't know then. Yeah, that was exactly the same. If I put some arbitrary address, right, like a string that is not in the dictionary, like comment this out, the string is no longer in the dictionary, right, and now I say at s, which is this symbol right here, at s, find, it should give me a 0 on the stack, but it doesn't, it gives me 1c2. It is possible that it doesn't realize that it's a comment, like it's not recognizing comments correctly and actually assembling that. That can't be right. That shouldn't be right. On C2. I mean, this did work. What are we doing? What does it do? It. Start with S on the stack. It's possible one of these codes are wrong. I mean, this exact same code is working on this version of the VM, so it should work on this version of the VM. And if the fact that it's not indicates that there's something wrong with this VM, right? So something is going, in my mind, is something wrong here. Or I kind of just eliminated the idea that I that I miscopied it or somehow corrupted the. I mean, obviously this code is even worse, even less legible than it was originally. Like this is illegible, but I had to put it all in one line, and now it's even more illegible. But still, this should work. All right, let's do this. All right, this is demo, yes, and then T is still ename, right? Ext. Okay, are these two the same? S, T, are they the same? Okay, so something's wrong there. Because that should run this program. And okay, so if I make J, say add s, right? I think I did this earlier. I think something's wrong here. Right. So if I type this right here, it works. So now the test is, can I make a function that does that? And return. Oh, am I missing a return somewhere? Probably not. No, because the queue has return. Okay. Q is I mean, this thing is using that register. It is using the S register, but it's also saving the contents of the S register and restoring it afterwards. So that it should be perfectly safe to use that register. But maybe I should give it a different register just in case. So we'll call this B, and this B. I hate these names, right? Like bad. Right, we'll say BW demo. Okay, right. And now our B, and I'm looking for. All right, so we'll make another copy of this. So A, right? A is 04. I want 4 letters, but let's call it demo. Then now I have to change one letter to. So now if I say A, B, are they the same? A, B, Q, and nothing goes on the stack. But if I say A, I know that puts a 1 on the stack. So this part works, and then something in here is going wrong. Because it just disappears. So I am able to run Q, but then it just disappears off the stack. What does it do? Okay, fetch the value of t, push it to the control stack. Now whatever's on the stack becomes t. There's two values on the stack. So in that case, b is now t. So or t is now b. So if we say t and we say b, right, it successfully restored it. So and it successfully restored this. So all this stuff is working as it should. Like, I know this works. The logic here is right because it works here. Something is wrong in the virtual machine implementation, or in the in the code that's invoking a function. But why would it be wrong? Right. So if this is true, then we return t immediately. If this is true, E could be wrong. I had a feeling E was wrong, like earlier, and I never followed up on it. Now you have to learn about my assembler. Okay. All right. So dot I is an if. All right. So we're in an if statement, and look at the code here. So we're going to say there's some value on the at compile time. There's some. No, sorry. At compile time, what this does is it pushes the value of here. You put here, sorry. No, it doesn't. All it does is it compiles an empty spot. Which is what this does. So it calls it recursively calls this function. Yeah, it's kind of silly. It puts the address. So H0, it puts an H0 thing. It's hop if 0. So at runtime, this is going to look at the stack and say, if this is 0, I'm going to make a hop. And a hop is a relative movement of the instruction pointer. And then this macro puts this here. So it says hop. And then puts 0, hop 0. And then when the else comes, right? So when the else comes, what this does is it actually puts the, so it says hop. So at runtime, you're over here somewhere. Like, forget this. I'm imagining there's more code over here, assembly code over here. Whatever, you put some value on the stack. If that value is 0, you're going to hop. So you're going to hop. If there's an else, then you want to hop to that else. So if it's 1, you pass through this, you lose the value on the stack, you hop over this number, you do some stuff, and then you get to the else. Now you're done. So you're going to do an explicit hop to the end of the thing, to the then. This looks right to me. So here you want to hop either to the end, or if there's an else here, then you want to hop to this spot, right after this spot. Which is what hop here does. Hop here takes the address that we've assembled so far, and it fills in this blank, and then this one fills in this blank. So depending on whether we put an else there or not, this looks right to me. I'm fairly confident this is right. So let's say, just call this like less than or something like that. Let's just test it. So we're going to say we have two numbers on the stack. We're going to say less than, if true, and then we'll put the number 99, and then else, and we'll put 22, and then just arbitrary things, and then. All right. So I'm testing now that this macro works by compiling it. Let's see what it emitted. So here's the less than. Less than, hop forward 4 spaces if it's less than. So hop over everything. Oh, wait. No, if it's 0, hop over everything. Why is there a call in there? This is wrong. Okay, so I now suspect that the problem is with the if and then compiler here. I can't believe 5 people are watching me debug this. It's weird. Okay, I'll try to make this comprehensible. So what I expect to see is, here's the B and the W, and the return. The at B is actually showing up as this because that's the ASCII value of this bytecode. Here's my less than. Here's the hop 0. Here's the distance to hop, which is 4. Control D is 4. But then where is this call coming from? Oh, call is this is the value of 99. 99 is the call. So let's change that to like 9 or something, so I can see it better. First of all, it should be like load byte 9, else load byte 22. All right, so that, I guess that's the 9 and that's the 20. Let's set it to 1, and so we have A and B. So this is the start of the function. Less, so it's going to say it has 2 values. If it's less than, it's going to, if less than is true, then it's going to fall through and it's going to load the byte A, and then it's going to hop over to this byte right here. And so there needs to be a return here. Yeah, so the return. So and it's going to hop over 5 bytes now. So 1, 2. I think this number is wrong. Like the number that it's hopping over is wrong. And I can't step through it yet because I don't have a debugger. That was the whole point. That's why I wanted the debugger. I can't step through and see what it's doing. But like we want to hop over. Okay, so if it is less than, then we want to do this. If it's not less than, oh, okay, so we need to hop over this 1, 2. We need to hop over 1, 2, 3, 4. Yeah, this is off by 1. And then here, we have a load byte. All right, so here we want to hop over. So when we get to this point, so if it is true, we want to hop over 1, 2. And it's saying hop over 3. A, B, C is 3. Control C is the hex code for C for 3. I think that's my issue, is that this is an off by 1 error in this. No, it's in 2. A minus slot minus 1. I think this is what I want to do. I think I have an off by 1 error here. Assembly language is no fun. I don't enjoy this at all. But I would enjoy it a lot more if I had a good debugger. Panic, okay. No, that's no good. Wait, why do I get a panic? Why are they the same? Okay, so now when this runs, we get a panic instead of that. So let's comment this line out. Let's just get back here. Okay, so the question is, when I run, right, that panics too. Well, okay, I actually, can I do this? How do I do this? How do I set the instruction pointer? I'd have to say, I should just expose this, right? I should expose this as a thing I can say go to or whatever. Mod go to is, oh no, I can yeah. So we'll say mod go to this. Because I think I actually can step this if I can set the instruction pointer and then tell it to run. Remove this, copy this. Okay. Okay, so see the instruction pointer is at 100. Let's run this. Or 100. Instruction pointer still has not moved. 1CF. Okay, so I want to set the instruction pointer to 1CF. And I can do that by saying MB4 go to and I have to parse this number because I don't know what it is. Parse. All right, now it's at 1CE, okay, which is right before it was what I want. So now when I hit step, oh, underflow. Oh, right, because I haven't put anything on the stack yet. So I need two things on the stack. So we'll say 5 and 6. Put those on the stack. No wonder. Okay, so now we step. Restore this again. I guess I can actually assign this now from the virtual machine, but I don't know how to do it. I mean, I know how to do it. I just don't know the right numbers to put it. Yeah, because the instruction pointer is stored in here somewhere, so I can set it that way. I just haven't exposed that with a nice user interface yet. All right, so my instruction pointer is at 1CE, is right here, right before this. Oh, but okay, hang on. Here I definitely need to put 1 plus this. Because goto is meant to be used inside the system, where it's always being called inside of a step, and the last thing a step does is add 1 to the instruction pointer. So there's an implicit -1 in there. So I need to add the 1 here. All right, so now 1CF is exactly what I want. So 1CF is the less than. I have 2 numbers on the stack. I hit step. There should be no underflow here. I'm frustrated because this little box is not drawn here. So let me fix that real quick. The problem is that IP used to be the instruction pointer used to be a top level like variable, and so you say vm.ip, and now you don't have that because I moved it into the machine. So now I don't know how to get the instruction. Well, obviously I do because it's printing out somewhere, but let's see. Somehow I'm managing to print it, but so I must have a way of exposing it already. Show IP. Oh, I see. So I have it this way, but I don't have it to just like give me the number. Okay, so okay. So one more time, we'll copy that over. And so now, when I draw this thing, so I'm going to go to the script for this card, and it says IP. So now we're going to say get IP. And now, when I draw this again, it should actually show the, yeah, it's at the right spot. So I run this, boom, there we go. And then I'm doing some magic here to do this. Run this, and now when I view the page again, it should have moved that all the way down here. There we go. Now we're cooking. All right, so we're going to say 5, 6, and I've manually moved the instruction pointer here. So now when I say step, this little thing is step. It should move to the next one. So it should do a less than. 5 is less than 6, so it should put a 1 on the stack. -1 for true. Yes. And I would have expected it to increment the instruction pointer. Which it has, but it didn't update this. Okay. Right, so that is something I have to fix here in the prototype. And I need to do this. I need to have this button send that same message. I didn't copy that, did I? Ah. Stop. Copy this. Go here. Go to the prototype. And then on every button, it's on click, show RAM. Yeah, it used to say show RAM. It needs to do this instead. Okay, so now it's already done that, but let's refresh this again. Put 5 and 6 on the stack again. We're gonna hit a step. Right, because I didn't do the I want to let's do it manually here. I want to expose this so I can write it from assembly language, but I don't know. Too much trouble right now. Okay, so we're here. We have, I don't know, I must have done something that hit a return statement. So let's move from the control stack back to the data stack. So we have 5, 6. Now we want to run this code right here. If I say step, moves to H0, that's correct. All right, so the number is -1. Hop if 0. So if we're 0, we're going to hop. Otherwise, it should be on the LB. Right, so we're going to go to LB. Yes, that's correct. And then we're going to push A to the stack. You know, the number 1 to the stack. And then we're going to hop. And we should hop to that return. It just didn't hop at all. What this says is we're gonna jump to the current instruction pointer plus 1. No. Current instruction pointer plus the value that is right after the instruction pointer. Basically add this to the instruction pointer. I told it to hop 2. I didn't tell it to hop 2. The macro told it to hop 2. So it's here, and it adds 2, and it gets to this. You needed to hop 4. I'm going to have 2 off by 1 errors in this case. This is fine. All right, let's swap it. Let's explore the other branch here. So we'll run this again, reset everything. Again, put this where we want to go. And we'll put 6.5 here. So now it's not less than. And now we're going to step. And the hop 0 should take us where? It should hop 1, 2, 3, 4. So 1, 2, 3, 4. We want it to land on the LB. And it's again two numbers too small. So one is that I introduced a bug here, and I probably did it the wrong way. That's probably what happened. So in calculating this jump, where I did here, I said -1 should have done +1. And that's my off by 2 error. Okay. So let's do this. What I need to do is have tests for all this stuff so that it's all working beforehand. And you can debug it as you're building the thing. I have tests for most of these ops, including, but not for the instruction, or not for the assembler macros, which are these .I and the if and then and all that. All right, so now I think this might work. I put the 2 on there because if it's less than, then put a 1, else put a 2. Not less than, so put a 2. 5 and 6. Well, then we should put a 1 up here. I did. Okay. I think that was it. I had an off by 2 error. So now I believe if and else are working. And I think this basic logic was right. And it was only the hop logic, this logic in the hop 2 somewhere. I think that was wrong. So now I think there's a possibility that everything just works. So where did I have the problem here before? Try this. So what I'm seeing is that, let's remove, none of this executes. This is all garbage now. We can put it in like a, I don't know if I need to save this or anything, but little scratch thing. what I'm seeing is it says -1 should be on the stack. The goal and the t should be the same. So goal is should be a string, right? Oh no, they're not. Right. Okay. So it's not that goal and t should be the question is wrong. Where is it? Goal and t are not the same, but rather the goal is the entry that I want to find, and the ename is the string behind it. So the string for that entry and t should be the same. And if that works, then 1 should be on the stack, and it is. So now let's put t there and then find it and see if it finds the address. Oh, it underflowed. Okay. All right, so I am going to wrap this up. I don't want to sit here and just debug this all day because this has already gone on too long, and it's gone from a a useful stream of information to just sitting here watching me debug stuff. But I will come back at some point and do the. I don't know if I'm gonna do this on camera, but I'm gonna my next bit of work is to get a real debugger working. So all the stuff I'm doing here, I'll be able to do that, interactively rather than type set the IP or set the instruction pointer to this and do all that, and then I'll be able to debug this because I'm doing two things at once. I set out to build a debugger, but I'm also in the process of explaining this. I've been fixing a few things and then actually trying to get this to work. I mean, I did do some work on the debugger here, so this and these buttons are the debugger in question. It's just this should be part of it too, being able to invoke a set an address to start at and all that kind of stuff needs to be in the UI. I mean, like, really, it's not that hard. I could do that, right? Couldn't I? Like if I have a get IP, why don't I just have a set IP? I think this is like on RG is probably Oh, RG is a list of registers. It is an array. So if I get the IP, set the IP, so it's really just set IP is equal to X. So we got to put some. We'll call it A for address. All right. So I will just real quick stick this here. And then this can be removed and this can be copied. Okay. And then what I'm going to do is I'm going to make a field. And I'm going to call this the IP address or the instruction pointer. And script is, maybe I'll even, I was going to say animate it, but I wanted this to be something you could set. So script on change val do I don't necessarily want it to change while you're typing. That's fine now. It's fine. Text, so we'll do that. On change val do MB4 set IP. I'm going to set it to, do we want this in hex? Yeah, hex parse. No, format. Oh yeah, parse. Parse the value that we have here. And then we can turn on X-ray and just click on this thing. Oh no, we can't. There's overlapping things here. So I had to click on this little part of it over here to get that button. Otherwise, I was clicking on some other. And then B4 step to cause that to refresh. All right, go back F1 to go back here, and I say 80, and there it goes. There's my IP address. Instruction pointer. All right, so underflow. Okay, first of all, one thing I want to do is when I run this, what do I call this? Is this called IP? Yeah. This is a field called IP, and then when I go to here, I'm gonna turn that X-ray off so I can read. Get IP and is it card.ip? No, it's card.widgets.ip. Card.widgets.ip. Because I'm using name IP here. I want to say card.widgets.ip value is going to be equal to the hex format of this, and probably let's give it at least four digits, and we'll make it uppercase because everything is uppercase here. So now, as soon as I press F1 or click this to go back here, that should update to the current IP or the current instruction pointer. 100, it did. Not 4 digits though, so I did the wrong kind of formatting. I think you have to say 0.4. Let's look at the manual. Format. So the formatting language. Oh, that's decimal places. So add it to at least characters. 0. So I need to say 0.4 to make it 4 digits. Right here. Yeah, there we go. All right, so make this a little. I'll put a label on it. It's always visible. New field, and we'll call that go to or instruction pointer. It should be the same as up here, right? Oh, wait, this is the label, and then this is the text that I want to do, and we'll make it no border, and we will make it transparent. It's so transparent. This is one thing I really like about Lil is you can just like build the tools while everything is still running. It's just nice. Kudos to John for that. Okay, so boom. Oh, panic again. TF. So it did not find T, so we'll did get that far, but it didn't. So that's actually the thing that is doing the panic. Yeah, underflow. Somehow F is wrong. Again, I'm not going to try and debug that now. I just wanted to put the this little debugger in it so that I could do that. And it might be nice to be able to like type in, you know, at T or something like that, or I don't know. We'll see. All right, but so let's run this. And then we can say at f, or let's look at where f is. We'll say 13f. Okay, so 13f. And now we're there. We didn't scroll to this point though. Might be nice to scroll to that. We'll do that later. So this little symbol here, the greater than symbol, is the way it's rendering that this right here. I don't know. So like I said, my next step is I really want to debug this, and I also want to not write it like this. I want to be able to take the code like this and see it like this, maybe even syntax highlighted if I could. That might be a stretch, but I definitely like to see a better display here and step through it and figure out what's going on here. But I'm not going to try and debug this now. I've been at this for almost 4 hours now, so I think I'm going to stop and go say hello to my little girl who came home while I was doing this, and come back later. So everyone who was watching this, thank you so much. I really appreciate it. And you can subscribe to this channel, or if you want to know more about this and like kind of join the place where I post lots of updates about this. It's at tangentcode.com. And if you click on community, there's a link to a Discord here. So that's where I post stuff about this almost every day. I also post to Twitter, and I'm TangentStorm on Twitter, and you can find me from there. So yeah, thanks again for watching, and